Welcome to our, I guess this is our second in-person class and our third actual lecture in person. And I hope everybody was okay with the Zoom-only lecture last time. This is, I prefer actually seeing you, and I can't, you can't choose to turn off your video unless this was, I think I mentioned last time, unless this was a Black Mirror episode and you could actually turn off yourself live. So you can't do that, although I guess some people may be waiting for the YouTube lecture to actually watch it, in which case then I can't see them. But anyway, so this is lecture, is this lecture 2? No, this is lecture 3, sorry. This shouldn't be lecture 2, this is lecture 3 here. Let's change this to 3. We have the date right? So the 21st, yeah, we've got the date right. The 21st. Okay, a couple of announcements before we begin. Announcement number 1 is that, of course, homework 1 is due this Friday at 11:59 p.m. on Canvas. I hope everybody started it, and I hope everybody's posted questions if they have any on Canvas. Actually, Chandrasekhar, you're here. Yeah, so this is our second TA. Chandrasekhar, do you mind standing up for a second, just waving hi? Hey, so this is Chandrasekhar. He and Niraja are both here, and they are eagerly waiting your questions on Canvas to help, as am I, on Canvas. But anyway, just to remind you, I hope you've all started the homework already. Could you raise your hand if you've started your homework already? All right, excellent, very good. So you folks are together. Maybe the folks who haven't come wouldn't have raised their hands. So the other thing I want to mention, of course, is that I'll have an office hours this week, this Thursday at 10 p.m., which is the night before homework, which generally is usually when people want to talk to me. It's just before homework is due. So that will be open for you. And it starts at 10, but I'll go as late as you want. I could probably start it at 9:30 if 10 is too late for you. So let me know if you want to start at 9:30. I can do that too. And then Niraja and Chandrasekhar, do you have office hours yet? Have you posted it to Canvas too?
Yeah.
Okay, great. So that you've seen the office hours. Can you just remind everybody when your office hours are? Monday 8 to 9?
Monday.
So that's Chandrasekhar. Monday 8 to 9, and that's on Zoom?
Yeah.
Okay, and then Niraja, when's yours?
We conducted together yesterday, but if everyone wants separate hours, we can.
Yeah, I think you should try to do it separate. That way, if you spread it out, then it gives more people opportunity to come to office hours. If it's at the same time, then it's focused. So I'll do Thursday night, and you guys choose some other time that you both can make it, but it shouldn't be the same thing. So
Wednesday 8 to 9 is.
Wednesday 8 to 9 would be great, especially this week, because I think people would come. Okay, great. Here's our roadmap, and so what we're going to be doing today is continue our discussion of bias and variance, and talk about regularization, and then talk about a couple of ways of essentially achieving sort of a nice trade-off in bias and variance, and we're going to talk about that in the context of linear regression with a regularizer, and we're going to start off with a very simple regularizer, which is the two-norm regularizer, and that's going to lead us to ridge regression. We'll also talk about cross-validation and what all of that is, and then we'll finish up with multi-class classification and what is that, and we'll generalize logistic regression to do multi-class. I'm hoping actually we have multi-class listed next week, but I'm hoping to finish that up today. So we'll get a little bit ahead. Okay, some source material that we drew from, some readings. By the way, so I updated the overfitting and underfitting write-up. In fact, I updated it a little bit earlier today, so if you've got a version of that sitting around on your laptops or phones or something, maybe grab another version. Just a few minor typos and fixes and stuff, so feel free to download that again. Okay, so here's our sort of overall overview, which we keep looking at. We're going to be looking at this every day, or every day that we meet, and we're kind of here. We're in this section here. And we're here. And we're also here. We're here. And we're a little bit kind of here. So we're kind of doing a lot of different things at the same time. And then, of course, we're doing this as we go along. And your homework is doing all of this stuff. Let's see. And then I guess as we move along, we'll be touching on these applications. And then I think last week we actually did have a little bit of discussion on philosophy as well. So we're beginning to touch different aspects of this. So this is, again, our overall model of what machine learning is. It's a form of indirect programming or indirect algorithms where rather than programming a computer directly, we program a computer to program another computer to do a task. And that is essentially what machine learning is, basically. It's a form of programming once removed. Yeah, question.
So those, the algorithm / computer program,
Yep.
Are those kernels for convolution?
It could be. I mean, it could very well be, but it could, like for example, convolution typically would be something that we might code directly. You know, we might code it, but on the other hand, it might be a library. Actually, it's a little bit even trickier than that because maybe we might do a search algorithm to find the fastest convolution.
Okay.
But then the convolution itself, however we achieve the operation of convolution, might be part of what's needed during the learning phase to produce, say, the learned machine learning program, which is kind of represented there. And then the idea is that once you've got this stuff here, that's the thing. You know, like new data would come in, it would use this, you know, program, and this is the way the program looks. It looks very different than a computer program. It looks like a bunch of weights or coefficients, and maybe we could plot them using color. But when we have a machine learned program, it looks very different than, say, a human written program, which looks something more like this. This is MATLAB, but here is something that a machine learned program is a set of coefficients, or maybe it's a set of symbols or something else. It's not really something that's easily interpretable. Of course, people are working on trying to interpret it, but it's not something that's really designed to be interpreted by humans, unlike a programming language like MATLAB or Python or C++, which is designed to interface directly to the human. The constructs in such languages are designed to be manipulated directly by a human, whereas these programs, you know, the things that are learnt in response to the program that does the learning, and also given data, which is another ingredient in, because you know, data is really important, and also given a computer and given an optimization procedure, like maximum likelihood estimation, then you get something that doesn't at all, you know, lend itself to easy interpretation. Of course, a lot of people are trying to figure out and say, okay, well, I want to know why did Netflix recommend this movie to me? You know, and it's not very satisfying. The machine learning system is not very satisfying. It says, here's the answer, and you say, well, why is that the answer? Why are you recommending this to me? Or why are you making this decision? Or why did the self-driving car decide to turn left here? And if you can't analyze it, you can't ask such questions, then it makes AI systems much less useful.
Okay. So this is like a visual representation of the weights.
Yes.
So these would be like theta?
For example, yeah. So this could be a visual representation of all of theta.
Okay.
For example, like, you know, the weight. So, and this is an example of maybe like a deep neural network, and one layer of a deep neural network. This one way of plotting it would be in terms of receptive fields. But there's lots of ways of visualizing theta. Usually it's done in some sort of image-like thing. So this is one way of doing it.
Okay.
So that's actually a very good point. Maybe we should just put a big theta here. And, you know, say we're using theta. Usually we use theta or W to indicate the weights, so the things that we're learning. For the most part in this class, so far we've been using theta, which is right there. In fact, here's a simple linear model where basically input is the input is x, and the output is h theta of x. And in this case, it's a linear model, so we just do the dot product, and we assume an objective function which measures how well, given a data set, this thing here measures how well h is doing. So we have a training data set of XY pairs, and if that thing J is big, then that model under a particular value of theta is doing poorly. And if this thing J is small, then it's doing well, we assume. And how do we find a theta that does well? Well, we use gradient descent. That's a very common strategy for learning. It's like it's just basically high school calculus. We just use high school calculus, except it's in the multivariate case. And we take gradients of this with respect to theta, and we formula the gradient and set is equal to 0. And in this particular case, we can just actually set the gradient directly equal to 0 and solve it exactly. And we get, we saw we get the normal equations in one case. We also saw that we can get batch gradient descent last time, where we sum up, where each time, in each step we repeat something t times, and each time we essentially sum up and compute the entire gradient, and then adjust the parameter theta by alpha times the gradient of the objective. And that's gradient descent here. And then that leads to this kind of solution where pretty much if this is theta space, like this would be theta 1 and theta 2, we would be marching along until we get to the minimum, if there is a minimum. This is the linear model, so in this particular case it's very simple and very easy to find the minimum. For more complex models, it doesn't look quite this nice, and there might be multiple local minima, like one may be there, and one may be there, and one may be there. But in this particular one, there's only one global minimum, and everything is nice and convex. And so no matter where you start, you end up in the same solution here in the middle. Stochastic gradient descent is a case where it's the pretty much some variant of stochastic gradient descent is the technique that's used for all successful AI systems, and that's rather than computing the whole gradient as you do here, like this is the entire gradient, we just take one term at a time. So rather than summing for I is equal to 1 to n, we have another loop around here, as you can see. We have an inner loop, and we sum over all of our data items for I is equal to 1 to n, and then we update theta incrementally. We incrementally update theta for each data item, compute the gradient of the objective just when that one data item is present, and then we march down, hopefully in a way that actually does well, and in practice it does extremely well. And in terms of efficiency, in terms of like the most work done per floating point operation in general in practice, this is the method, or some variant of stochastic gradient descent is the method that works by hands down the best. Yeah, question?
So for stochastic gradient descent, we update theta sample by sample.
Yes.
But for batch gradient descent, we don't update theta at all until we calculate the gradients of the entire, batch of samples.
That's right. That's right. And then there's also mini batch gradient descent where it's in between. It's not sample by sample. It's not the whole thing, but we take a group of samples together. I mean, when you think of this objective here, this objective, right? So that's the overall objective. I mean, this is in the linear case, in the linear model case. So that's the objective. We can take the gradient. Now notice that all of the data is involved in this objective because we have the sum for I is equal to 1 to n, and n is the number of samples. And so we're trying to minimize that objective, and that's what learning is. So full gradient descent would basically just take the gradient of this thing. Stochastic gradient descent would choose some order of the data items, and each time it would take the gradient just of each term, just the gradient of each one, and then move a little bit in the direction of the negative gradient. And then mini batch would be we chunk these things together into chunks, and then take the gradient. And so we'd kind of like have gradients. I mean, we had the equation in the last discussion, lecture 2. In fact, maybe I wonder. Yeah, we can actually go to lecture 2. That's one of the great things about slides is that you can. I think we can actually go back. Actually, do we have it? Maybe not. Maybe I should. Maybe it was lecture 1 we did it in. Anyway, you get the idea, hopefully. So that what's happening is that we're not summing over everything. We're not just doing one sample, but we're doing a group of samples at a time. So the other thing we looked at last time was logistic regression. So when the thing we're trying to predict, y, is a real number, then linear regression makes a lot more sense than when the thing we're trying to predict is a binary number. When we know that we're trying to do binary classification, where it's buy or sell, or left or right, and we have a choice between two options, and we have to make a choice. A better strategy is to actually say, okay, the output of the classifier has to be a number between 0 and 1. And in fact, we can give it a probability to say that the output of the classifier is the probability of 1 or the probability of 0. And so the standard way of doing that is to use a logistic function, which has this form. So this is the definition of a logistic function. Well, actually, this is officially the definition. G of z is the definition of a logistic function, and this is the example of logistic regression. And what logistic regression does is it, rather than using the output of theta times x directly, we put theta times x inside of the logistic function. So we get 1 over 1 plus exp to the negative theta transpose x. And so that's something that is guaranteed to be between 0 and 1, because the logistic function is guaranteed to be between 0 and 1. When z is negative, you get 0, and z is positive, you get 1, and then it goes from 0 to 1 in a smooth fashion. And how smooth it is depends on a coefficient. Right here, there's no coefficient there, but last time we talked about, I think it was the coefficient of beta. So we can actually stick, I'm not sure, I don't think I have that slide, or maybe I do, but we can stick a beta there, and then that, do we have that? Yeah, no, we don't have that slide here. Oh no, we do have that slide. So here's the logistic function with different values of beta, and you can see that as beta gets larger and larger, here's beta is equal to 10, we make a much sharper transition, and when beta is small, like 0.05, we make a smooth transition. And so in some sense that you can think of beta as kind of like a form of confidence. Like if you're really sure, and you really want to make a sharp transition between this point and this point, kind of like, remember that picture of the cliff? Like there's the ocean, and then there's the sudden cliff, and then the land. If you really want to make a sudden change between ocean and land, then beta or the logistic function should have large coefficients, so that it makes a sudden transition from 0 to 1. If, on the other hand, let's say that you live in southern Louisiana or something, and there's a period of we have bells at this university, in case you haven't noticed. So it transitions from sea to land somewhat gradually. So it's ocean or gulf in that case, and then it goes to marsh, and where it's kind of somewhere in between land and ocean, and then gradually it becomes land. And so that's an example where beta would be small, where you don't want to suddenly you don't want to suddenly transition from 0 to 1. You want to maybe you don't want to be certain. Yeah, question.
So would you say that a sudden transition will make the model overfitting?
Yes, we're going to talk about that. We will talk about it. So like, if you're too sudden, and we talk. I'm going to mention this again when we talk about overfitting. We're going to go back to that because I want to hit on that point again with respect to logistic regression, because I think last time we didn't do that point justice, and I want to do that. I want to spend a little more time on that this time. But yes, you're exactly right. But the thing is, like, sometimes, like, let's see if we have this thing here, right? So this is an example. This is an example of where we're using logistic regression, and the colors are not coming out that well here. But maybe let me just turn off the lights for a second. See, you can see the colors. Can you see the red and the black? So you can see that you've got red lines. You've got the red line is the logistic regression function, and you've got the dots. You've got some zeros and you've got some ones, and you can see that the zeros continue on even after the ones start. So there's this region where there's this uncertainty. Like, we don't really know, and so do we want to pick any one point that makes a very sudden transition in our logistic function between 0 and 1? Probably not. Probably we want to say that there's this region of uncertainty. And the region of uncertainty would be somewhere around here, where we're saying, okay, well, we want to more slowly. I mean, this is not particularly slow, but it's certainly slower than than say if we were to go here and then do a sudden transition up, like a step function. And so that region of uncertainty makes sense because, after all, like if a machine, humans express uncertainty. Humans should say they don't know when they don't know. It's actually something that I mean, you guys are older than the typical high school student, right? But I mean, when you're young, you're kind of afraid to say you don't know, and you're afraid to express lack of confidence. But then as you grow older, you start realizing that the world is nuanced, and you're willing to say I don't know. And saying you don't know or being uncertain about something is actually more accurate. It's a more accurate way of conveying your thoughts, because if you force yourself to say yes, if you're at 0.50000001 and then you say 1, or if you're at 0.4999999 and you say 0, that's a loss of information. You're losing information about how certain you are about something. And machine learning systems also should say when they're not certain. Like if you're doing a machine learning system for your company or something, and it's trying to make a decision. Let's say you're an investment firm, right? And you want to build a binary classifier, buy, sell, and let's say it's a $50 million trade or something. So it has huge consequences. If the answer is 0.50001, where you really don't know, but you're saying okay, let's seal that to 1, and you make that decision, and it's a catastrophically bad decision. And you go back and look at the classifier and it said, well, it's set to buy. But then you look at the probabilities and you say, oh, wait a second, it was right at 0.5. It really didn't know. We should have looked at that. So, I mean, investors are aware of this. I mean, if you do any investing, this is a notion of like volatility or uncertainty. And so things like that, you don't want to, you don't want to not pay attention to the uncertainty that's inherent in the problem. And you want models to express uncertainty. And so probabilistic models in general, and logistic regression is one of them, is able to express uncertainty. And so for this example, in this region, you want to say here, well, I'm really not sure if it's 0 or 1. And if you did say you were sure, it would be incorrect. I would argue it's incorrect. And the life message is never be afraid to say you don't know about something. I'm certainly not. So if you ask me a question, that's actually one thing that teachers, like beginning teachers, like when they first start teaching, they're afraid to say they don't know. But when teachers become more seasoned and experienced, and someone like asks me a question that I don't know, and I'll say I don't know. I mean, I'll try to find out the answer and come back the next week and give you the answer. If it's about auto repair, I probably won't. But if it's about machine learning, I will definitely. So it has to be relevant, of course. Right? So all right. So where are we? So Right, so here's the logistic regression. This is a logistic function. One of the things that's great about the logistic function is that its gradient is really easy to compute. The gradient evaluated at z is just the logistic function times 1 minus the logistic function. We derived that last time. And this is a property actually of a lot of sigmoid functions besides the logistic function, but it basically means that doing things like computing the chain rule is great, right? Because it makes it really easy to do chain rule type computations and gradient type computations. It's one of the things that computationally makes it much more attractive, and mathematically too. So how do we actually how do we train in logistic regression? Well, we just like always, we have a training data set, and we use a probability model. And this is again what we did last time, but we compute the likelihood, and this is the likelihood. The likelihood sums. I just noticed a typo. So n, we're usually using n as the number of data points. So I is equal to 1 to n, where n is the number of data points here. So that's also, that typo exists in last week's slides too. So I'm trying in this class to keep the notation throughout every lecture as consistent as possible, because it's annoying when you change topics and suddenly the notation changes. So this is the likelihood, and now notice that we can, when it's a likelihood, we want to find the theta that maximizes it, right? So likelihood is the thing we want to maximize. Cost is the thing that we want to minimize, and so we can take the negative of the log likelihood and define a cost, which is usually represented the negative log likelihood. Now, one thing you might be worried about is, well, what do you mean, like a financial cost? No, we don't really necessarily mean it's a cost in financial terms, but it is something. We use the word cost to represent something that we want to minimize. We use the word value to represent something we want to maximize. We use the word likelihood to represent something that we want to maximize. Yep,
I
question.
actually did some research about the likelihood online by myself. I'm not really sure if I'm interpreting it correctly. So this likelihood means how likely is the distribution of our model fitting the entire, actual distribution of the data.
That's right. So a likelihood, we usually, like in general, we write this as the likelihood of the data given the parameters, right? And that is defined to be the probability of the data set under the parameters theta. So it is sort of treating it probabilistically and says, okay, so if I've got a model and these are my current parameters, how probable is the data for these parameters? And maximum likelihood basically says, okay, well, what I'm going to do is I'm going to use a probability, but I'm going to change the probability of the data by changing theta. And I'm going to make the data that I saw. Because after all, the data that I saw, you're trusting that data that you saw. You're assuming that data that you saw is really drawn from some probability distribution. And if you're trying to learn the probability distribution, then it should be the case that the data that you saw drawn from that probability, that's what happened after all, right? And so if that's what happened, that should be reasonably probable, right? If what you saw is not probable, like, imagine you have a biased coin with 0.9 and 0.1. 0.9 is the probability of heads, and 0.1 is the probability of tails. And you flip the coin 1,000 times, and it's mostly tails. So that's not a very likely draw. That's a very improbable draw. It's a possible draw, but it's very improbable. So what you'd like to do is if you have, you'd probably, if you're hypothesizing that 0.9 is the probability of heads, and you see 90% tails, you should change your hypothesis. You should say, wow, I was wrong. I got to update my belief about the probability of heads being 0.9. And if you are perfectly respecting of the data, and if you have 90% tails, then you would change it so that the probability of tails would become 0.9. And so that's no different here, where you're saying, okay, I see this data, and the data can be any form. It can be real valued or integer valued or whatever, or a value of xy, a data set of xy pairs like we have here, and then you change theta so it makes the data probable. That's the maximum likelihood principle. And then you can just say, well, if I take the log of the likelihood and I take the negative, I'm not going to do that here, then it becomes like a cost, which you want to minimize. So here's the likelihood of the logistic regression model for this data, and it's a function of theta, our parameters. And if we want to make the data likelihood, we should find a theta that makes the data likely. And if you want to minimize cost, you'd find a theta that makes it least costly, that decreases the cost, because we don't like costs. We don't like spending money on stuff, right? We want it to be as cheap as possible. That's why we minimize costs. So here's an example of this thing we already saw. We talked about uncertainty. And here's, one of the things that's, we talked about like linear versus logistic regression we talked about last is that if you try to use linear regression to learn this data, you'll get a different transition point than if you use logistic regression. And logistic regression in this case actually gives you better accuracy. You learn, and the reason why is because as you move away from this transition point, you're paying a big penalty for these points far away from, you're going farther and farther and farther away. None of these points are ever getting above 1, but the linear model is getting bigger and bigger and bigger. So these points that are very far away from the transition are having a big effect on your error. Whereas when you have logistic regression, once you're already saying 1, these guys shouldn't matter, right? The only thing that should matter is doing the thing around this decision boundary. And we talked about the margin. Remember the margin? And we did talk a little bit about support vector machines, but we talked about the margin of the classifier, and generally what we care about are the points that are closest to the margin, and those are sometimes called the support vectors. And so in this case, these guys would be the support vectors. We also saw how the perceptron, which is a very early learning model, which was inspired, it's a very early neural network, and logistic regression were sort of one and the same. Logistic regression is like a soft perceptron, and the perceptron came out of our understanding of neurobiology at the time, and logistic regression came out of statistics. And people were working on pretty much the same thing without knowing about it. And that was long before the web. And so you could be down the hall and you could be working on the same thing, and you had no idea that you were working on the same thing because you have different terminology. But the perceptron was kind of like logistic regression, except that rather than a smooth logistic function, you have a step function that goes, it's basically this. It has a hard activation function, which is kind of like the logistic function with extremely large beta. So it makes a very sudden transition. In fact, here it makes an infinitely large, so it would require an infinitely large beta. Or equivalently, it would require very large magnitude values of theta. We're going to talk about that in response to your question about overfitting in the perceptron in a minute. And then, in fact, here's overfitting and underfitting, and we saw this in the case of polynomial fitting. Like we got a set of points and we want to fit a polynomial. We can actually underfit, where if we're forced to have a line, it's very unlikely that this set of points comes from a line, although it's possible. We have a quadratic, which isn't perfectly, it's not perfect, but it does minimize the error, but it doesn't overfit. It doesn't do what a fifth order polynomial does, which fits it perfectly, and probably overfits if it's the case that there's a bit of noise in the data. And this is also, I think, a pretty interesting example about a real-world consequence of overfitting, and how about the Fukushima nuclear reactor earthquake estimate differed by 12,700 years, depending on if we overfit or not overfit. And it had real-world consequences, and that quite catastrophic worldwide consequences, all as a result of overfitting. So this is a real problem, and as machine learning systems become more and more, I mean, imagine like making a cancer diagnosis to a family member, or misdiagnosis. Imagine if it was the case that because of overfitting, you were misdiagnosed to not have cancer, and so therefore you started treatment years later than you should have had you had a correct diagnosis. That could be 10, 20 years of someone's life. And so you really have to focus on these things. You have to worry about overfitting and underfitting. As we proceed with machine learning being used in real world systems, we need to be more and more focused on these sorts of things. This we already saw just today and last time. So this is getting back to your question. So you remember the logistic regression we saw. This is two-dimensional logistic regression, where we've got zeros over here and ones over here, right? And you can think of the ridge, like there's a like if there's the cliff, it sort of goes down here. I'm not very good at three-dimensional drawings, but hopefully you can get the idea. So like over here, maybe this is the sea, what's blue, and is there a brown color? Yeah, maybe this. So this is the land over here. And the logistic, it's two-dimensional logistic regression, so basically it's 0 over here, and then it goes up to 1 over here. And the question is, how smooth should this be? Should it be very sharp, like the cliff off the western coast of England, which is like where I think that picture came from, or should it be smooth, like the Louisiana marshes? Now, let's look at the likelihood function. Okay, so here's equation 2.3, and this is the thing that we should have talked about last week, but I want to do a better job talking about it this week. So we've got the likelihood function. Actually, this is the negative log likelihood function. So it's a cost, and so in this particular case, we want to minimize this thing. So what happens as the cost decreases? So let's say these are our points. So these are our 0 points, and these are our 1 points, right? And when it's a cost, these are the ones. And this is the prediction for the ones, and these are the zeros, and this is the prediction for the zeros. And why is this the 0? Because when I is a 1, then 1 minus I is a 0, and this whole thing doesn't matter. And when yi is 0, then 1 minus yi is 1, and this stuff doesn't matter. So what's happening is that in order what's happening is we're trying to minimize this, and so in order to minimize this, we need to have the log of this thing be 0 and the log of that thing be 0. And the way to make a log of anything 0 is to set that equal to 1. So what it's trying to do as hard as possible is to make this to be exactly equal to 1 and to make this exactly equal to 1, right? Which basically makes this exactly equal to 0, right? So now the logistic function looks like this, right? So no matter how sharp you are, notice that like on this plot, none of these things are actually 0 down here, and none of these are actually 0 here. They're like 0.9 or 0.999 or 0.99 and so on and so forth. And what's going to happen though is as we keep training more and more and more, it's going to try to make this as close as to 0 and try to make all of this stuff as close to 0. So you might start off with this, but as you train more, you're going to get this logistic and then this logistic and this logistic and so on and so forth until it's going to just keep getting sharper and sharper. And it's going to get, and like a plot doesn't really do it justice, right? So, but you can imagine it's going to continue to train until it becomes, if it was a pure mathematical model, if we were using real numbers as opposed to fake numbers, like floating point numbers, in computers we don't use real numbers, we use fake numbers or floating point numbers. If it was a real model, then what would happen is that the logistic would get sharper and sharper and sharper, right? And then, so then it would eventually, attempt to, it would eventually make this truly 0, truly 1, and make this truly 0. But how does that happen? The only way of doing that is if the values of theta become infinitely large. So what happens when we're using floating point numbers when theta becomes infinitely large? Well, we just get infinity, and we get numerical error, and we get floating point exceptions. Right? So like computers can't, there is a representation of infinity, but as numbers get bigger and bigger, you're going to get overflow error or underflow error. Right? And we're going to lose precision, and it's just going to be, and then the numbers are not going to mean anything anymore. It's just going to be noise. And so what happens is that, maybe it's not supported. So just purely maximizing likelihood or purely minimizing cost has some problems, because as theta gets larger and larger and larger, it becomes a more and more sharp model. And sharp generally means more and more complex. And somehow the magnitude of the elements of the theta vector represent the complexity of the model, like how sharp it is. And you could kind of think of complexity as sharpness, right, or curvature. Like if it's a very sudden change, that's a more complex model than if it's a very smooth model. So it's a notion of complexity. So maybe what we want to do is do something in maximum, when we're doing maximum likelihood or minimizing cost, do something that keeps the theta from keep the elements of theta from getting too large. Right? And that's regularization. That's the omega thing. Right? So what we really want to do is we want to say something, let's say here we're minimizing cost. So we like subtract omega of theta, right? And that says, okay, well, if we want to minimize cost, it would be plus omega. So we'd also want to minimize complexity. So omega is something that measures how complex the model is by theta. And we're going to talk about that. So generally speaking, you do need to do some sort of thing. This is also known as regularization, which we will talk about very soon today. But I wanted to talk about this, review this here to make sure that it's clear, because it will lead into something else, which is also bias and variance. So remember we talked about bias and variance and underfitting and overfitting, and how what we're doing is we're fitting a model to some data, and underfitting corresponds to high bias and low variance. And underfitting is when a model is too simple, right? Like what if it was the case that we forced theta in the previous example? Like what would underfitting be? Underfitting would be to say, okay, at the outset, sorry, you cannot use a value of theta. We cannot have any of your elements of theta be greater than 1 or negative or less than negative 1. It has to lie within the range +1 or -1. And then you train it, and then eventually maximum likelihood gets stuck, right? It says, okay, sorry, you can't get any larger than 1, and you can't get any less than -1. But then you're saying, but wait a second, you're misclassifying all these points, right? It's like, you're so smooth, you're doing a terrible job. You're saying probability 5 when the data supports probability 0.995. So that's a form of underfitting in the logistic model. That's low complexity, right? And so it never matches, another way of looking at it, it never matches important characteristics in the data. In such case, it's biased. It's said to be biased. And notice that even if we train on multiple samples of the data, they're all drawing from the same distribution. So I'm getting Slack messages. Let me just turn off Slack. My last class, whenever I was getting a lot of Slack messages, somehow it broadcasts the Slack sound. Does anyone use Slack? Right, so it broadcasts the Slack beep sound all over the room. So every time I got a Slack message, you'd hear speakers going, everywhere. Some people jumped out of their seats every time I got a Slack message, which wasn't so great. So, but I can turn it off on the phone. Okay, so, okay, sorry for getting distracted by Slack. So here's what we were talking about. So we have multiple samples of the data in logistics. So it's kind of like saying we have multiple data sets that all kind of look similar to this, right? They're similar to this, and maybe they have the zeros on one side and the ones on the other side. They're not all at the same position, but because if we're forced to have every theta be have magnitude no greater than 1, then all models are going to be the same, no matter what the data looks like. And you're going to have low variance. The models are not going to vary from one training set to the next training set to the next training set. That's bias and underfitting and low variance because the models are not going to change. The opposite is overfitting, where you have you can say, okay, let's let theta get as large as it wants. So one data set you're going to get very different values of theta than another data set, and each time you do a training, you're going to get very different models. And each time you train, you're going to train on the idiosyncrasies, the unimportant idiosyncrasies that exist in the data, which is not good because basically then when you go out into the real world and you launch your model, you deploy your model out in the real world, it's going to fit all of these idiosyncrasies in the training data that don't really exist when you actually use your model. Okay, so bias and variance. We can derive it mathematically by using the error. We can say, okay, what's the error of the model? So the error is taking the expected value with respect to the true distribution of the prediction minus the answer, right? And we're using the squared error here. And so we just expand it out, and we complete the square, and we have this term, and then the cross term, and then this term. And so we can write it in this way. And so last time we just said it was equal to this, and we said, well, look, this thing cancels out because this guy here is equal to 0. The second term cancels out. And I wanted to add a little bit more. I think the discussion we did last time could be improved, and so I added a few other equations here that explain exactly why the second term cancels out. And so here's just the second term. Let's go through this because this is not officially review, because this is a new information. So if we look at the previous slide, we're just looking at the expected value of the second term. So that's what we're doing in this next slide here. The expected value of the second term. Well, the first thing we do is we take out the 2. We write out the expected value explicitly in terms of the integral. And then here's the second term without the 2. And we distribute the things involving y as far as we can inside of the integral, and so we get this thing here. Right, but now all of a sudden we say, well, look, this is all for a fixed x inside this integral. X is fixed, and this is a constant, and so we're just taking the integral of py given x of minus y, but that just gives us this, which is e of y given x. So this whole thing here becomes this. And so this e of y given x goes there, and the rest of it becomes the ey of x, and so it becomes something minus something, which gives us 0, and that's why the second term cancels out in all cases. Okay, so what we end up getting is 2 terms. We get this term here and the inherent error term. And notice that we're trying to understand the bias and variance in terms of the model that we're learning. But the model that we're learning is not involved in that second term. So that's something we cannot minimize. It's the inherent error, it's the inherent uncertainty in the problem. And what we're going to talk about Bayes error probably next lecture. And so this is very much related to what's known as Bayes error. It's kind of like light speed. It's like if you're doing a probabilistic model, there's a certain inherent error that you can never improve upon. And again, assuming probabilistic, it's a probabilistic model. So we can't deal with this. I mean, what I should also mention, actually, when I say we can't deal with it mathematically. What we can deal with it is practically, because oftentimes, where does that actually come from? It comes from things like errors of sensor measurements. So let's say we stick sensors around a room, like temperature sensors. We could either use low-quality sensors or high-quality sensors. Low-quality sensors would be less costly, but they give you noisy readings. And we could spend more money and get very high-quality sensors that use really good devices and that have been controlled and vetted and so on and so forth. But they're more expensive, and so we can control this using physical means, but we can't control it using mathematical means. The first term, however, we can control by machine learning, and it's notice that the best predictor is again E of y given x. That's what we expected before, because when we take the gradient and set it equal to 0, that's what pops out. And so when h of x is equal to E of y given x, the thing that we can control is 0. But we can't do that, so we want to sort of express things in terms of bias and variance. And so how do we derive that? Well, we add another form of 0 here, where we take the expected value. And now here what we're doing is we're taking a random subset, a random training data set. So d bar is a random variable consisting of another draw of training data. And every time, and so it's kind of like a probability distribution over data. And so we take the expected value of the learnt model, or at least in this case, h of d bar given x, and we're adding it and subtracting it. And we're doing the same trick. We complete the square. And again, the second term cancels out for reasons that are similar but not exactly the same as before. But one way you can easily see it in this case is that here you're taking the expected value of the data of this guy, and that guy's already over here. So you get this minus this, and so this part here turns into 0. And so you get this. After this whole thing is gone, you get the first term and the second term. The first term is known as the variance. And let's just zoom in just to make sure that everybody understands what the variance really is. So the variance is saying, this is all for a particular x. It's saying that for that x, this is the expected prediction for x. This is the current prediction for the data set d. And then we take the square of the current minus the expected, and then we take the expected value of that square difference. And that's a variance. It's basically saying how different do different trained models do on a given data set, on a given sample x, when you train it multiple times over different data sets. That's the variance. And if it's the case that it always makes the same prediction for x, then the variance is going to be 0. And what the bias is saying, okay, well, here's the best we can do. But I mean, that's not the true answer, right? Because the true answer might be random. But this is the best answer, the one that minimizes the squared error. And the bias is saying for x, how far away am I from the best we can do, squared? That's the bias squared. And then usually for like doing the bias plus variance, we average over all x, weighted by the probability of x. And we get this classic picture. This is the classic machine learning picture where as model complexity increases, you can see that the variance goes up and the bias goes down. This is the bias squared. And the overall error is a combination between the two. And this is the best point here. So as the model complexity goes up, this is overtraining, this is undertraining, and this is just right training. All right, so too hot, too cold, just right, as a function of model complexity. All right. And pretty much all machine learning systems, from simple linear models to the most complex deep model, has this kind of behavior in one form or another. Now, where it gets tricky is how do you measure complexity? Because Complexity can be measured in things like how many parameters you have, or how capable the parameters you have, or what features you fed to the model. But complexity can also be measured in things like what algorithm you're using to train the model, or properties of the data. So complexity is itself a very complex concept. So there's the complexity of complexity, which you have to consider. But the big picture is that as complexity, using these multifarious different ways of measuring it means the variance will go up and the bias will go down. Okay, so that's the review. So as we do at the end of every section, I stop lecturing until somebody asks a question. Yeah, question.
This D-bar stands for the mean, because you said it's going to be a random data set, but I remember, from the last class, you mentioned that D-bar stands for, the mean that we got from the entire model that trained by the specific data set.
Yeah, so here's why we're using D-bar. So, take a look at this thing here. It's only for notational clarity. So when we have this quantity here, we could write it. It's kind of like a scoping rule. It's kind of so let's say you're programming. And do you program in C?
Yeah.
So let's say you do a curly brace and you call a variable called I. So then that I lives in that block started by that curly brace. But now you have a nested curly brace inside of it, and you have a new variable called I. Right? So then you use I inside of the inner block. So that I refers to the inner I defined, not the outer I. Right? So we could do that same thing. So we could, it's kind of like, in fact, let's use D. So what we could use is, I could have a curly brace and say, int D. And then I have something else that says int D. And then here's the close of the inner block and the close of the outer block. So when I refer to D here, it refers to this D. Right? It doesn't refer to this D. Now, going back, that's really small. It's too small. So, sorry. So, if you're doing C, right? If anybody's a C programmer, so there's the inner D and the outer D, and whenever you refer to D in this inner block, you're referring to this D and not this D. And even though the variables are the same name, they're different Ds, right? So going back to this equation here, what we could have written, which I thought would be confusing, is we could say the expected value of D of H of D of X minus the expected value of D of H of D of X squared, right? So which D is this D? That's not the same D as this D. This D is this D. This is kind of like the definition. We're taking the expected value of a random variable called D, and it's applying to this thing. Now, what if we had two Ds here? That would be really confusing. It's like, well, which D is which? Is that the inner D or the outer D? So what we're doing is we're just kind of going back to C. We're going to call this guy D bar. So C's happy with that. Programmer's happier because now you know it's D bar, or let's call it E or something. It's kind of call it something different. And so we're just calling it different, so that there's no ambiguity that this D, we're taking the expected of this random variable, but it's exactly the same probability distribution. Like if I have two fair coins, if I sample one or sample the other, if I take the expected value with respect to one or the other, you're going to get the same answer because they're identically distributed. And so we just have two identical random variables, just with different names, that are defined here only because of the scoping, because we want to emphasize that this D refers to this and not this one, but this D does refer to this. Okay, does that make sense? All right. I've seen books do it like this, and I personally think it's a lot more confusing when folks do it this way. Because again, it's a scoping thing. It's like good mathematical notation is as important for math as good programming practices are for programming. Okay, any other questions? Yeah.
How do you relate this curve to that MSC? Like I'm having a hard time understanding.
So you've got this term here. Sorry, keep asking the question. I'm already answering it. So is that, like, how do you relate the curve?
Yeah.
So this is the variance here, which is this guy, and this is the bias squared, which is this guy. And some way or another, we're measuring the model complexity of H, right? And we will see examples of this, right? In fact, we're about to see an example soon. We're going to see an example of how do we measure the complexity of H. We already actually kind of saw an example. Like one way of measuring it would be how big are the values of, what's the absolute value of the theta values, right? So in other words, we're saying if, let's say theta is a vector of length 10, right? So if theta 3, the third element of theta, was 10,000, that would be a more complex model than if theta 3 was 1,000. So one way of measuring, not the only way, but one way of measuring complexity is how big the coefficients are. Right? But there's an innumerable number of ways of measuring complexity. And in fact, to this day, people are looking for better ways of measuring complexity. But that is one way that's been very effective. And the other thing about it, as we will see, is that it's very easy to do. Mathematically and computationally, it's very easy to work with that, with things like magnitude of values. But so all we're doing is we're changing the model complexity, and we're saying what happens. That generally speaking, as you're allowing, like let's use that. Let's say that the magnitude of the theta is how we're measuring complexity. So as you're allowing the values of your learnt model theta to increase, the variance of your learnt thing is going to increase. And as you're restricting the coefficients of your model from increasing, the variance of your model is going to decrease, and vice versa for bias. I mean, imagine like you've got the ultimate restriction of theta, where you say, find me the best model, but theta can't be anything other than the zero vector, right? Your variance is going to be 0, and it's going to be great, right? You might think, so this part of my error is going to be 0. And you might think, okay, well, I've got small variance. Is that great? Does that mean I'm going to get good accuracy? No, because your bias is going to be big, and it's like a balance, So and you want to find the right balance between the two, the one that minimizes the overall error, which is there. Question?
Yeah. So I could see how having a large theta would cause complexity and overfitting in the logistic regression, but for like a polynomial kind of thing, would the theta show up in the exponents?
Well, no, the thetas are not in the exponents. Because like in the polynomial thing, it's like you've got let's say it's a fifth order model.
Yeah.
Right. So you can imagine that if you're allowing theta to be unboundedly large, you're able to fit more things. Right. The model has more flexibility. It's kind of like saying, I allow you to run from here to there. That's less restriction than if I say I allow you to run from here to here. So the more you allow the coefficients to be bigger, the less restricted the model can be, and the more it's possible to fit pretty much anything, even in the case when it's not logistic, when it's linear regression.
I would have thought that the order would play more of a role in like over complexity, and the coefficients would just be necessary to either shift it up, shift it out, or like match the points.
The order of what? I'm sorry.
The order of like the polynomial, if we're doing like a...
Oh yeah, no, the order is also a notion of the complexity too. Absolutely. The order is, so remember we said that there are lots of different ways of measuring complexity. And one of the ways we said was the features that you use. Mm-hmm. And the order of the polynomial, like one of the things, going back to, the lecture one was, the part of what we do is the whole notion of feature extraction. All right, so like when we're here, dealing with features, feature selection, feature engineering, representation learning. Generally speaking, as we add more and more features, the complexity goes up. And so the order of the polynomial is exactly analogous to that, because if we're allowed not only x squared, but x cubed, and x to the fourth, and x to the fifth, and so on and so forth, or xy, or x squared y, or xy squared, or x to the cube y squared, and so on and so forth, if we're allowing all of that stuff, that's kind of like more and more features. And the model complexity also increases. So some people I mean, one simple way of measuring the complexity is just the number of parameters. Like as you add more and more features, or more and more higher and higher order, theta gets longer and longer, right? But that kind of doesn't really, maybe one feature is itself more powerful than another feature. Like maybe x cubed is more flexible than x somehow, but there are lots of different ways of measuring complexity. But one way of measuring, like if you fix the order, there's still ways of measuring complexity amongst just the values of theta, and that's what we're talking about. Like the features are fixed. But in general, both. You have to think of the input to your model, the value of the coefficient, and the structure of your model. Like if it's a neural network, it might be like the number of layers of your neural network, or the width of your neural network, or the type of nonlinearities you use in your neural network, or the type of algorithm that you use to train your neural network, all of which contribute to overall what the complexity is. Like I said, dealing with complexity is a complex thing. There's no one best way of measuring complexity. But the concept of this. How do we go back? Go to page.
I was just thinking like large thetas meant you were dealing with large order of magnitude data versus, and I wasn't thinking of it in terms of like being like able to overfit something because they're just coefficients, but I suppose that limiting it would probably limit its ability to overfit.
Absolutely, large coefficients also contribute to measuring complexity. Like in this example here, the larger the coefficients, the smaller the cost becomes. And if you really want to have cost of zero with logistic regression, cost absolutely, numerical, actual, real value zero, the only way to achieve that is with infinitely large theta.
Yeah, this one, it makes sense to me because theta is in the exponent, so that would be kind of like an order kind of thing. It was just confusing me.
In the linear case.
Yeah.
In the linear case too. I mean, it's, like I said, there's lots of ways of measuring complexity, but even in the linear case, like imagine if you put restrictions, say you want to be a linear model, but you can't be too big. That limits your model. It limits the flexibility. I mean, a good example is to think about the extreme case, right? So, like in the extreme case, when you say the thetas cannot get greater than zero, then the bias is going to be large. The variance is going to be zero, and so that means like you're way over on this side, right? So the variance is going to be zero, but the bias is going to be huge. Now that doesn't mean that it's the best. Like you could say, okay, well, I'm allowing my theta to be, if I have a linear model and my theta can be infinite, does that mean that the model can do anything? No, it's still a linear model. Right? So if you want to have a more complex model, you have to go to a nonlinear model. And so linear models are great. I mean, linear models are actually great for two reasons. One, because they're easy to analyze mathematically, and they're super fast. They're just great because they're speedy. And logistic regression is also really fast. I mean, that's not much different. And if speed is the most important thing. Like if you're trying to get something to work on your phone with really low energy, and you don't want to consume battery, you really should be and people still use linear logistic regression for like really low power machine learning apps, just because they're fast, they don't require any energy, and they're easy to train. That itself is a trade-off. They're not the most accurate models, but they still are quite useful. Okay, so let's talk about Occam's razor. So Occam's razor is a very famous property that is often mentioned in machine learning, and it's often attributed to William of Occam, who in the year 1324 said plurality should not be assumed unnecessarily. And William of Occam was a monk, I believe, and Occam's razor is generally meant, is sort of a general philosophy of pretty much everything, or all scientific endeavors, not just machine learning, which basically says that when you're trying to explain the data that you see, and you have multiple ways of explaining it, and they all explain it equally well, one should prefer the explanation that's the simplest, the least complex. But actually it turns out that Occam's razor goes back a little bit earlier than Occam like St. Thomas Aquinas in the 13th century, which is the year 1200, or 1200 something, said that if anything can be done adequately by means of one, it is superfluous to do it by means of several. For we observe that nature does not employ two instruments when one suffices. And this is very early on. Very early on there wasn't much technology back in the year 1250. But then if you go back even farther to Aristotle, to 350 BC, Aristotle said in a memorandum called Posterior Analytics that we may assume the superiority ceteris paribus, which means all else being equal, of the demonstration which derives from fewer postulates or hypotheses. So we may assume the superiority. So these are sort of fundamental philosophical principles that one generally can apply to almost everything. Like when you're reading the newspaper and there's disagreement, and maybe there's arguments on both sides, and you say, well, what's the simpler explanation versus this more complex? If all else being equal, you might just go with the simpler one because it's more likely to have happened. There are fewer simple explanations than there are complicated explanations. Why are there fewer simple explanations? Because they don't take that long to describe. And if something doesn't take that long to describe, it's just there aren't that many possible things that could not take a long time to describe. There are a lot more things that could take a long time to describe than there are things that take a short time to describe. Because things that take a short time to describe take a short time to describe. And they're just not enough. You just can't. Like, I can't explain machine learning to you in one sentence. Right? I mean, if you came and you said, I want to do machine learning. Actually, this happens a lot. Like sometimes at the very first day of class, you get questions from students, and I say, well, you have to wait. The whole class is what's going to answer that question. And so it's like there are some things that are complex that take a long time to describe. Anyway, so it turns out that this was also mentioned again by Einstein. And this is kind of a very nice and profound way of saying it. And Einstein said, the grand aim of all science, not just machine learning, is to cover the greatest possible number of empirical facts by logical deductions from the smallest possible number of hypotheses or axioms. Right? So that would be translating it into what we've been talking about, small values of theta, or low order models. Right? We want to learn and put restrictions on things. We want to come up with a simple explanation. So that's the idea of Occam's razor. And so generally speaking, you want to use Occam's razor for almost everything involving machine learning and AI. So let's apply that principle to this little exercise. So we've got a table of numbers, x1 and x2, and a function, an unknown function h of x1 and x2. Okay, now don't look at the slides, don't cheat, don't look ahead, and I want everybody to really think about it, because you have the answers right in front of you, so those of you looking at your laptops, please look away. And look up here. And those of you ignoring me, please stop ignoring me, and please look up at the screen. So basically, when x1 is 3 and x2 is 2, h of x1 x2 is 7. When x1 is 5 and x2 is 4, h is 23, and so on and so forth. H of 7 6 is 47. H of 9 8 is 79. And the question to you is h of 10 9. What is that?
98.
98. Okay, so does anyone think it's anything other than 98? 99. So how many vote for 99? And how many vote for 98? Okay, and did any of people who voted seen this before? If you've seen it before, you don't count. So let's do it again. Who has never seen this before and votes for 99? And who has never seen this before and votes for 98? Okay, so I think the 99s beat it by one vote. The 99s, so I think we have 5 votes for 99 and 4 votes for 98. Right? Okay, so why 99? For those of you who didn't vote. We could come up with a relatively complicated formula, right? And so one way of saying this is to say, okay, well, one thing that fits the data is to say, well, we could multiply x1 and x2 and add x1 from the previous row. All right, so like, for example, we could say, 9 times 8 is 72 plus 7, which is 79. Right, and 7 times 6 is 42 plus 5, which is 47. And 5 times 4 is 20 plus 3, which is 23. Right, and so therefore, 10 times 9 is 90 plus 9, which is 99. Right, that's a formula that seems to fit. Right, but it involves some assumptions. Right, it involves, first of all, saying, okay, well, it basically says I need to use the value from a different row. Right, now h is a function of two arguments, but maybe it has memorized the previous row. But at the same time, it's kind of complex because they're saying, well, look, it's 3, 5, 7, 9, which are all odd numbers, and suddenly we jump to an even number. And so in order for that to work, we're saying, well, so far we've seen the previous number, which is an odd, but now all of a sudden we've got an even, a row where the even, where x1 is an even number, and we're going back to the previous row, which is an odd, and all of the results that got us to deduce this formula were based on these all being odd. All right, number one. Number two, it's even worse because, well, we don't have any evidence for this 7. Right? What was before it? Well, we're making an assumption, and so there's some of the data that we're not using at all, right? Because we're sort of extrapolating beyond. So there's kind of two things. It's kind of complex, right? It's saying, it's using some weird pattern. Now, if we took random samples of data, and this was our random sample of data, should you try to make a deduction based on the idiosyncrasies of your data, and therefore come up with a complex model? Or maybe you could come up with, by the way, the 99 is the most popular explanation, and it was the case here as well. So when this is actually done, when there are surveys, most people, or I should say the majority of people, think it's 99, which is kind of interesting. Right, so what happens in the first row requires an assumption. I've already kind of said this. And it needs to rely on these non-regular pattern of inputs, like x1 and x2, which is an odd initial sequence, right? 3, 5, 7, 9, and then suddenly we've got a 10, and we're still using the same pattern. That seems like that should make you suspicious, you 99ers, right? So the 99ers should be suspicious and should say, I'm assuming, I'm using an idiosyncrasy in the data. The 98ers, on the other hand, may have come up with a formula that looks like this, which says x1 times x2 plus x2 minus 1. So it's a slightly more complicated formula in one sense because you have to subtract 1 from it. But on the other hand, it's simpler because you don't have to go to the previous row. And what that does is that leads, first of all, this works. Secondly, it works for the first row, right? Because if we do 2 times 3, which is 6, plus 2 is 8, minus 1, which is 7, which is what this formula. So we even get to use the first row. So in some sense, we get to use more data. We didn't have to throw away some of our data in order to come up with our hypothesis. I mean, imagine if a machine learning model, like, it's got all of this great data, and in order to learn something, you need to throw away 25% of it. Would you trust that machine learning model? Like, a machine learning model decides to ignore 25% of the data. There might be situations where that seems reasonable, but that also seems to be worrisome. Right? That's a lot of your data. I mean, maybe throw away 5% of it or something. I mean, your data would have to be pretty noisy to throw away 25% of it. And it's not throwing it away for good reason. I mean, you're throwing it away just arbitrarily because it doesn't fit your hypothesis. That's the reason why there are lots of reasons to throw away data, but that's not a good one because you come up with a hypothesis and this inconvenient 25%, toss it. So that's bad. Whereas in this guy, you don't throw away any way of your data, and it's simpler. And it's simpler because, like, well, yes, it is a -1, but it's a major drastic reduction in complexity because you don't have to go to the previous row, and you get to use all your data. Okay, it turns out that there's an even simpler formula, which is x1 squared minus 2. So now you've completely ignored x2. I mean, so in other words, you can get something that completely ignores this column. That's even simpler, right? And you can still fit the data perfectly. And it still leads to 98, by the way. Right? And that might be even the best one because you're saying, I'm making the fewest assumptions about my data. I'm coming up with a formula that fits the data and that doesn't rely on things. Now, this is actually also interesting because generally, when we're doing a machine learning system, like we talked about the order of the model, like should we use x squared or should we use x cubed or x squared y cubed and so on and so forth. Should we use all these features? The more features we add, the more possibility we have of overfitting. And the fewer features we have, we reduce the possibility of overfitting. And so here, what we're doing is we're coming up with a model that perfectly fits the data, but is even simpler. We've completely ignored one of our inputs, and we're still perfectly fitting the data. So if we were to use, say, Occam's razor, what would be the right thing to do? And so we have three things that fit the data. The first one kind of doesn't fit all of the data, right? And it makes a different prediction because it ignores 25%. The second thing does fit all of our data. And the third thing fits all of our data, but it's simpler. So what would Occam's razor say? Which one? I mean,
Third.
the third. All right. So we would probably fit the third because it's the simplest. This is the simplest explanation. And that's the idea of Occam's razor. It perfectly fits and it has the fewest number of assumptions. Now, what's interesting, and this is sort of going astray a little bit from machine learning, is why do humans tend to prefer the more complicated one? What is it about humans? Even though, generally speaking, like when you try to do scientific discovery, we strive for simplicity, but the general populace seems not, at least not in this case. So that's something to think about. I don't have an answer for why, but it is something to think about and ponder about weird humans that prefer complexity. So, okay, so then, in this particular case, when this is the support data, should we then truly minimize the cost or maximize the likelihood? And then what would Occam's razor say about this, where we have a very sharp transition at the boundary? Why should we prefer that one? Why not this decision boundary? We have this decision boundary and have a sharp transition here. Or why not, this one? They all perfectly fit the data, right? What would Occam's razor say in this case? Would Occam's razor say, let theta be infinitely large, and then you'd have this choice of all of these things that perfectly fit the data? How would you even choose amongst these infinite number of models, all of which have infinitely large coefficients or as unboundedly large coefficients? Occam's razor wouldn't say that. Occam's razor would probably say, well, make it as smooth as possible, but still fit the data well. So, you have pretty reasonable separation here. So you probably prefer something that does, kind of smooth, something like that, right? So how do we do that? So the way that we do it is with this idea called regularization. Now, regularization, we've already seen it before in the context of omega. In the overfitting document, in anticipation of talking about regularization, we even talked about regularization. We talked about a way of measuring complexity, which is omega. When we're doing maximum likelihood without regularization, is that we have some optimization problem, and the optimization problem involves error. If it's error, we want to minimize it. If it's cost, we want to minimize it. Oftentimes, it's called risk, and we want to minimize the risk. Or if it's called likelihood, we'd want to maximize it. Or if it's called value, we'd want to maximize it. But whatever you call it, and whether you're minimizing or maximizing, it's all pretty much analogous. You shouldn't see them as really being fundamentally different. It's just you're just trying to get something to fit well. And here's an example of cost minimization. So we find the hypothesis H in this hypothesis space, script H, that minimizes the cost. the squared error example was one where we can measure the cost of a vector theta using the sum of squared errors, right? So this is the linear regression case where we've got a linear model and we're basically trying to get this to be as close to this as possible, and to the extent to which the squared difference is large corresponds to the extent to which there is a high cost. Right, so generally speaking, when the model truly is unrestricted, and so that would mean, for example, in the linear regression case that we have, arbitrarily large theta and arbitrarily high order, minimizing the mean squared error has an infinite number of solutions. And which one do we choose? How do we choose from amongst this infinite number of solutions? Very much like what we saw in the logistic regression case. There's an infinite number. Some solutions are more complex than others. We want to have a simple one. That's what Occam's razor dictates. And so one way of doing it would be to just say, at the outset, choose H prime. And so that, like H prime, which is a subset of H. So choosing H prime might be, okay, you can choose any model you want, but the coefficients can't have magnitude greater than 1. That's one way of restricting. So let me just make sure this is very clear. So like we could say, as an example, this is an example. It could be that H is equal to all theta, such that theta is an m-dimensional real vector, right? And we could choose H prime, which is equal to all theta such that theta is still an m-dimensional real-valued vector, and that the max over j is equal to 1 to m of theta, of the absolute value of theta as j is less than 1, or less than or equal to 1. And you can see that theta prime is a subset of, H prime is a subset of H. That's one way of restricting. Putting a hard barrier is basically saying, okay, I'm putting a barrier by saying nothing can ever have a magnitude greater than 1. And that might be something we want to do. This general idea, just the general idea of forcing or encouraging, this is kind of like forced simplicity here. But whether you force it by saying absolutely positively you cannot have a coefficient greater than a particular value, or when you start paying some form of additional penalty during your optimization process, during your learning process, as you're learning a model, if you pay a cost for just having a complex model, no matter how good it fits your data, either of those strategies is called regularization. Regularization is the process of making regular or simple your model. So how do we do this? So here's regularized machine learning. So rather than minimizing the cost, we have a complexity penalty and a trade-off coefficient, right? So lambda is our trade-off coefficient. And it allows us to trade off, like, well, how much do we care about complexity? Or how much do we care about cost? If lambda is 0, then all we care about is cost. And if lambda is extremely large, then all we care about is complexity. And if lambda is somewhere between 0 and extremely large, then we can trade off. Now, okay, so if we care only about variance being small, what should lambda be? Like, all we care about is variance. We want the variance to be 0, or as small as possible. What should we set lambda to be?
0.
Any other votes? We want the variance. So remember, the variance means that every time we train a model on a different data set, we get the same answer. Right? So where's the data? Is the data involved in the complexity penalty? Do you see? Is the data is here? So if we want to get the same answer for any d, what do? we set lambda equal to, yeah, you greatly condense. So it's 1 over 0. You're close. It's 1 over 0, not 0. So it's infinite, right? So you set it to be extremely large. And so if you set it to be extremely large, what happens is that in some sense that guy doesn't matter, right? Because no matter what you do, if lambda is huge, the only thing that's going to matter is the complexity penalty when lambda is huge. Now, what if it was the case? So that would be so large lambda means low variance, but what's that going to do to the bias? The bias is going to be potentially huge. What if we want to have really low bias, but we don't care about the variance? Then what do we do? 0, right? Which is like 1 over 0, right? So then what happens is if lambda is 0, then this guy gets killed off, and all we care about is cost. And yeah, for every data set we're going to get a different learned model. But if you only care about variance being, if you don't only care about bias being small and you don't care about variance, then that's what you do. But if you care about both, you can set it. And so lambda itself is kind of a measure of how much you're allowing. Lambda is kind of like this axis, right? So lambda is like how much you're allowing complexity to happen in your learned model. And this is generally a really important thing. Like this is everywhere. Like every machine learning system has some form of regularization in it, which is some form of complexity penalty. So this isn't like a hard restriction to H prime, but what it is I think it's more like a discouragement. So this guy discourages. This discourages complexity depending on how big lambda is. And by the way, so I'll show you, remember that lambda is always greater than or equal to 0. So lambda is not, we usually don't use negative lambda value. So it discourages complexity depending on how big lambda is. And this is known as so the process is known as regularization, and this guy is known as a regularizer up here. We kind of already said this. If lambda is equal to 0, there's no complexity penalty. If it's large enough, we force the solution to be as simple as possible, irrespective of the data. The data, we don't care. Now that's not really machine learning. We could learn a model without having any data. Right? That's not going to work. It's going to have such a high bias. So an enormous part of machine learning, and pretty much to this day, what researchers in machine learning are still focusing on, a lot of researchers are focusing on, is how do you measure cost or risk or error? There's lots of different ways. Squared error is only one of many ways. Or likelihood when maximizing of the model given the training set. So how do we actually measure cost? Like, what is this thing? How do we measure that? How do we measure complexity? Like, is magnitude of coefficients the best way? I mean, that's one way. Or maybe that's part of a more complete strategy for measuring complexity. How do you consider the two together? So here, notice that they're additively combined, right? It's cost plus lambda complexity. Should they be additively combined? Should they be multiplicatively combined? Should we take the harmonic or geometric means? Should we take some other crazy kind of aggregation strategy between the two? Why should they be additively related necessarily? How do you do this in a way that leads to a feasible way of learning, right? Because you could come up with the greatest way of measuring these things in the world, but it's not computationally feasible to learn, right? Obviously, one of the big successes of machine learning recently has been the fact that we can train them, right? And if you propose something that's only mathematically interesting, that at the same time you can never try just because it's too complex, that's not, you never know if it's going to work. You also would like it to have good statistical properties, like good mathematical properties. Like maybe we can prove something about it mathematically, which would be great. And a lot of the strategies you can. But the main point is the many ways to do the above. And we're going to be studying some. In fact, we're going to study one in a slide or two. The other thing I also want to mention is that oftentimes, like remember we said a few slides ago, like in the logistic regression case, there were all these different lines that perfectly separated the zeros from the ones, remember? How do we choose between those two? Oftentimes, or how do we choose between those infinite number of hypotheses? Often what happens is that you'll find that a lot of models have the same cost, like the same lowest cost. There'll be multiple models, all of which have the lowest cost. So how do you choose the one? Oftentimes, this will choose one out of all of those, and it will choose a unique solution. One of the reasons why we often enjoy convex optimization is that if we can actually show that this whole process in equation 2.2 is a strongly convex program, then there's one and only one unique solution to this problem. Even when there's multiple solutions to the lambda is equal to 0 case, there's only one solution to the lambda greater than 0 case. Right. That sounded like a really heavy water bottle. So, okay, so here's our regularized learning. Any questions on this? Actually, we kind of already said this. We're doing things a little bit out of order. So, as lambda gets large, what happens to the bias invariance? And as lambda gets small, what happens to the bias invariance? So, we kind of already asked this, but as lambda gets large, what happens is that the bias goes up, the variance goes down. Let me write it just to be sure. So bias up, variance down. And as lambda gets small, the bias goes down, and the variance goes up. Okay, so that is now the end of this section. And so it's time to force questions on me. Yep.
Can we think of a scenario where both variance and bias are high?
Well, you can, in absolute terms, yes, but in relative terms, no, right? Because, they can both potentially be high, but what is high, right? The main point is high relative to what they would be if, say, you had more data or less data, or you had more complex or less complex. In general, one is going to, as you increase the complexity, one's going to go down and one's going to go up, right? So, but it could be the case that at any one point, if that's what you consider high, to be high. But relative to what values would be if you were to change complexity, then not really, no. They're really at odds. They're really at odds with each other. And that can be seen in the bias variance equation. So we said the mean squared error is equal to the variance plus the bias squared. So this is a constant. So when you have a constant is equal to a plus b, and both a and b are positive, and constant is positive, if a increases, then b has to decrease. And if b increases, then a has to increase. It's just like a balance. So they have to be, just solve one for the other. So variance is equal to constant minus bias squared. So they're in this mean squared error case, they're in a linear relationship with a -1 slope. So. Okay, other question? I'm not going to go on until you ask a question. Yeah, question.
I'm just kind of curious, when you do certain estimators, like mean square, maximum likelihood, right? If the data happens to be Gaussian, they all turn out to be the same. Is there anything, for if the probabilities are known, is there, that some complexity penalty is the right choice to make?
Yeah, that's a great question. So, yes. And the answer is yes. And we will be studying some.
Okay.
Right? In ridge regressions, like generally speaking, but it really depends on the kind of noise, right? So we can set up a machine learning problem, we can set up a particular model, we can set up the way that the noise is generated, and in certain types of noise, there's going to be an appropriate way of measuring complexity. right? And the way of measuring complexity would be choose the thing that has highest probability according to the noise, if you have the noise model. Right? And so it turns out that if it's a Gaussian, then the 2 norm is pretty good. It's pretty much what you want, and you'll see it in the ridge regression case in a minute. But it becomes more complex, right? Because if you're doing complicated face recognition with a giant 200-layer deep neural network, then the mathematics becomes a lot more complicated. Because first of all, you don't really know the true distribution. You don't know the type of noise it is. You're in very high-dimensional spaces, and high-dimensional spaces have their own problems, as we'll learn about. Like, I think next lecture, you're going to start learning about the crazy, ridiculous things that start happening in high dimensions. I mean, it's totally wacky what happens in high dimensions. I told you about like a 100-dimensional apple is a very weird apple, and we will learn about that. So you have to also be careful about cursive dimensionality of high-dimensional effects as well, which we will learn about. So this might be a good time. Usually I like to take a break at the 2-hour mark, but should we take a short break now and then go forward till charge to 10 o'clock? Okay, let's take a short break.
So for our homework, I feel.
Okay, folks. So let's now actually come up with an example of this. Our sort of first example of cost plus complexity penalty. And it's going to be called ridge regression. And ridge regression is actually also sometimes known as shrinkage methods. And the reason why it's called shrinkage methods is because what it's attempting to do is shrink the coefficients. It's trying to find the coefficients that still work but that are small or shrunk. And so the model, ridge regression still assumes that the underlying model, the thing that we're trying to learn, is still linear. So it's still a linear model in the sense that H, the hypothesis, is parameterized by theta, and the way that we get an output is theta transpose times x. But the penalty is going to be the magnitude squared of the learned coefficients theta. So here's the cost. Here's just the squared error first. So this is standard linear least squares regression given a data set. And when we did this before, and the thing that actually gives us the normal equations that we saw in lecture 1 was to use gradients and set this equal to 0, and we get the normal equation, and we find the Moore Penrose inverse, and so on and so forth. But what we're doing now is we're adding a penalty to this, and so this is the new term, and this is the 2 norm, right? The 2 norm is basically just it's kind of like the Euclidean distance of theta from 0. So if this is the axis, and we have theta 1 and theta 2, and then this is theta, the vector. This point is just this distance, the distance from the origin to where theta is. And here's the definition. So basically summing up the square of the coefficients and taking the square root of the results. 2 norm. So does that look like hopefully you'll see right away that here you have something which is a cost, right? Which is a cost. And here's a complexity penalty. And notice I'm saying a rather than the. Right? It is a cost. It is a form of cost. It is one of the many ways of measuring the cost, but it is a one. It is a reasonable cost. And we're also using the word a here. It's a complexity penalty. It is not the complexity penalty. It is a one. It is one of the many complexity penalties that, in this particular case, just basically sums the squares of the coefficients. And then we have, last but not least, of course, a trade-off parameter. Lambda, like we saw before. And this is known as ridge regression. So how do we do it? How do we solve it? It turns out that ridge regression, like one of the great benefits of ridge regression and this particular form of complexity penalty is that the solution to the problem doesn't become much more complex. And the solution to the problem actually is very nice and intuitive. So you remember, like when we did linear least squares regression, we got the normal equations, and we can solve the normal equations by finding the Moore Penrose inverse, which is this, times x transpose times x times y vector, where x, remember, x is the design matrix. And so x is basically this matrix, which consists of, x1, x2, and x of n. So we put the x, and this is an n by m matrix. There's m columns and n rows. So where every one of the input x's are rows of the matrix, and then we can just get the resulting solutions, the one that actually minimizes the squared error, just in this way. But now we've got a different objective, right? So now we've got that was when lambda was equal to 0. So what happens when lambda is not equal to 0? When lambda is greater than 0? And also, like one of the things we didn't really talk about was, this matrix. This is an m by m matrix, and for this to work, x transpose times x needs to be invertible. And when it's the case that when n, the number of samples, is much bigger than n, the number of dimensions, then it's very unlikely. I mean, if you're randomly sampling from a Gaussian, or if you're just collecting data off the street from somewhere, it's very unlikely for x transpose times x to not be invertible. But on the other hand, what if it's the case that you have m, which is much greater than n? So the number of samples is much smaller than the number of variables you're trying to learn. Like an example with maybe you for some reason you want to learn a very high order model, but you don't have a lot of samples. Right, so that's a potential worry, because you might overfit. In fact, there's a potential problem. Overfitting has a numerical consequence, which is that in such case, it's quite possible for x transpose x to not be invertible, in which case you can't even find a solution, because you can't invert that matrix. It's kind of like dividing by 0. So one solution to this, one way out of this is to regularize the problem and to add this complexity penalty, the 2-norm complexity penalty, or the square 2 norm. And the solution turns out to be very simple. It basically says that it's exactly the same thing, but before you invert it, you add lambda times the identity matrix. So lambda is an m by m identity matrix. It's diagonal, and it's always invertible. And if you make lambda big enough, then what's going to happen is this is going to be nicely numerically invertible. So it's x transpose times x plus lambda times the identity matrix inverse, and that becomes the solution. Right? And that's the ridge regression solution. It's still closed form, and it's still but the other thing, right away, and let's just zoom in on this for a minute. Just think about it in terms of bias and variance, right? So if it's the case that lambda is very, very big, right? What's going to happen? What's the solution you're going to get if lambda is huge? Is it going to be invertible? Yes, it's going to be invertible, but you're going to get theta is equal to what when lambda is very big? So think about it this way. So like when lambda is very big, this part doesn't really matter very much, right? And so it becomes kind of like this is gone, and you're doing the inverse of, what is the inverse of lambda I? That's equal to 1 over lambda I, right? You're just dividing by theta. And so if lambda gets very big, this part doesn't matter either, because you're just dividing by this giant number. And so all of the coefficients you're going to get are 0, which is exactly what you'd expect, right? Because if, going back to the objective here, when lambda is very big, what you're minimizing is this thing. And if lambda is big, this part doesn't matter. The only thing that matters is this. And in order to get this to be small when lambda is as big, is to set theta to be equal to 0. So the solution we get, the intuitive solution we see here when lambda is big, which is basically setting theta to be 0, the resulting theta, the minimum theta, is the one that basically, if theta is anything other than 0, then you're going to incur this huge penalty because lambda is so massive, right? And that better be the solution in the ridge solution. And sure enough, it is, because what we're going to be doing is just dividing whatever this is by lambda, which is going to, as lambda gets bigger and bigger, just give us a value of 0 over there. What if lambda is small? And if lambda's 0, then we're just going to get back the regular linear least squares solution, whatever it happens to be, and its corresponding numerical problems. Now, one of the things, like for example, you'll learn is that when you compute mathematically, either a matrix is invertible or it's not. It's a binary property. But whenever you're trying to do matrix inversion numerically, it's a continuum, right? It sort of slowly, it becomes more and more problematic. You run into numerical problems. You might get things, suddenly you might get numbers like 10 to the 308 or something. And when you start getting these giant numbers, chances are they don't make any sense. And they're just amplified noise, or amplified divides by almost 0. And what's going to happen is, as lambda gets smaller and smaller, if you're in this non-invertible case, what's going to happen is computing that inverse is going to create numerical problems, and eventually probably a floating point exception. If you have a good library for matrix inversion, namely a library that keeps track of numerical problems and reports them in an appropriate and understandable way, then you'll learn about these things. But if you have a poor library, then it'll just happily invert things and give you infinities, and you'll never know about it unless you look at it. So it's kind of you're sort of relying on the numerical library for doing this kind of thing. Now, Python's NumPy matrix inversion library, I think, is pretty good. So you're in good hands in this class. But on the other hand, you might be in an environment where you're required to use some C library someday. Let's say you're working with a company and you have to use the C library, and if it's not well written, it can be a problem. So you have to be worried. You have to be careful about that kind of thing. But mathematically, we say that as long as lambda is greater than 0, then it's always invertible, which is a mathematical statement. It's not a numerical statement. Okay, so here's ridge regression again. We've got the 2 norm. Now, one thing that's actually interesting is that we can look at ridge regression in a different, but turns out mathematically identical way. And this is a form of constrained optimization. So remember, we said that there was 2 ways of doing regularization. One way, we can actually have a penalty, right? And this basically says, this has a penalty. It says it encourages but does not enforce theta to be small, right? Like, as lambda gets bigger and bigger, and you're doing this minimization, so like you're minimizing over this whole quantity here. As lambda gets bigger and bigger, the encouragement for lambda to be small increases. Like when lambda's small, you might say, yeah, I think you should be small. And when lambda gets bigger, it's that you should definitely be small. And when lambda's really big, is that you have to be small, else you're going to be really in trouble. And then when lambda's huge, you're kind of like saying, well, if you're not small, you're dead, right? But in this form here, you're saying something different. You're saying, but it turns out it's mathematically the same. You're saying, find me the theta that minimizes this quantity, but only consider thetas whose squared 2 norm are no bigger than t. So this is a barrier. It's basically saying, absolutely, this minimization has to be done with this constraint. And you cannot violate that constraint. It's a hard constraint. But as long as you're meeting this constraint, all bets are off, right? You can do anything you want as long as you're meeting that constraint. So within the like, in some sense, this is kind of like, this is like a ball, right? This is sort of saying that theta has to live in, it's the 2 norm, right? So it's actually quite literally a sphere. So you're saying that theta has to live within an m-dimensional sphere, right? And the radius of the sphere, r, so you're saying that r is equal to t squared. Or sorry, it's the square root of t. Right, because for it to be Euclidean distance, you take the square root. And you're saying that as long as theta lives here, this is the 2-dimensional case where m is equal to 2, and this is theta 1 and theta 2, you're saying that theta has to be in this ball, or this sphere. Now, the claim is that these are identical problems, mathematically. It turns out that for any lambda, like if you're trying to solve the first problem, there's a lambda, if you're trying to find this first problem with some lambda, there's a t so that the bottom gets the same solution as the top and vice versa. And there's and this is basically the notion of, I mean, we don't have a lot of time to get into the details of the optimization, but it's basically Lagrange multipliers. And if we do Lagrange multipliers, we can actually convert the bottom one into the top. And vice versa, we can convert the top into the bottom. So the bottom line takeaway from this slide is that oftentimes you don't have to. There was last week, I think we had a question. Somebody suggested, why don't we just restrict H and force the hypotheses to only be within H, and you can't be out of it. Very much like what this picture suggests. Like you have the green zone, which is inside the ball, and the red zone, which is outside the ball. Right, and you can't be in the red zone. It's like this hard barrier. But it turns out that in many cases they're the same mathematically. And interestingly enough, by the way, oftentimes when you want to solve this kind of problem, you convert it into this kind of problem. Okay, any questions on that? So, any questions on this so far? Okay, so let's now add some noise. Let's say, okay, suppose the estimate's y. So here's our design matrix. Here's the true theta. So this is a contrived example where we're assuming that the data really is generated from a linear transformation of x plus some noise term where epsilon is basically Gaussian noise with so epsilon is Gaussian noise. It's zero mean and variance sigma squared. That's the same assumption we made last time. And so what we end up getting is the solution. So here's the ridge solution here, right? But let's put in the true answer and see what happens. Okay, so the solution, the true answer, y vector is equal to x theta star plus epsilon. All right, so this is now a random variable, and the randomness comes from the fact that this is a random, the noise is a random variable. Right, now we're going to actually see what happens. Like, what is lambda, what is the effect of lambda? And let's just, this is going to make it simpler. Let's say that we rotate the data in such a way so that x transpose x is equal to n times the identity matrix. And I know that seems like a strong assumption, but this will allow us to gain some insight on the problem, on ridge regression's problem. So if it's the case that we do this, and that it basically makes this equation that we're going to look at next a lot simpler when we make this assumption. So then what happens is that the ridge solution, it's a random variable, right? So there needs to be some randomness, is equal to n over n plus lambda times the true solution plus some random stuff, which is 1 over n plus lambda times x transpose times the noise. So a couple of things to note. So like if the noise variance is 0, right? So if this really is not there, then that doesn't exist. And we can see that we get the best solution when lambda is equal to 0, right? When lambda is equal to 0, we get the best solution because what happens is we get n over n and lambda 0, and so we get 1 times theta star. So we get the exact correct solution. Again, when there's no noise, when lambda becomes larger and larger, what's happening is we're shrinking the coefficients down because it's n over n plus lambda, and the larger lambda gets, the smaller the learned theta is relative to the true theta. That's why it's called a shrinkage method, because we're shrinking the coefficients down of theta star to the thing that we're using, that we've learning theta. The other thing to note is that, okay, let's say that there is noise here now. If we set lambda to be extremely large, we're going to get the same solution no matter what, right? The variance is going to be small because lambda is going to be large, and the thing that's noisy, this part, the thing that's going to change every time we run it, is going to be this noise, right? But if lambda is very large, the noise is going to contribute very, very, very little relative to this. That's the thing that's going to contribute to the most of the solution. So the variance is going to be very small. Of course, the estimate is going to be 0, so it's going to be a very biased, low variance estimate. So high bias, low variance. Right? Because the variance is going to be small when lambda is large. The bias is going to be large because we're going to get 0. But hey, if you want low variance, then set your lambda to be big. If you set lambda to be small, let's say you set lambda to be 0, then the noise, you're amplifying the noise as much as possible within the ability of lambda to do so. The way to get the largest noise contribution is to set lambda to be equal to 0, which means that every time you run it, you're going to get different noise and you're going to get different estimates. The variance is going to be large. Bias variance. It's perfect example of bias variance in the solution. Now, what's interesting also is that given, I shouldn't really say if we had theta star, because we do have theta star. We're assuming that we've got theta star. So given theta star, we can actually compute the expected error. Like, what's the expected error? The expected value of the squared two-norm difference between the thing that we're learning and the true answer, and it's going to actually have this quantity here. Because you might ask, like, well, there's bias and variance, but how do we get the best? How do we get the best trade-off? How do we actually minimize the error? So we can then get an expression for the expected error. And it's not too complicated. It's basically lambda squared over n plus lambda squared times the true answer squared plus this. Now, one thing to note is that as the dimensionality increases, the expected error is going to increase, right? Because as m increases, the expected error is going to increase. The other thing to note is as the amount of training that we've got, because n is the number of training samples, as n increases, the error is going to go down because we've got n over n plus lambda squared. So that's going to increase larger than this. And so as the number of training samples increase, the effect of the noise, so this is the noise, remember this is the noise term, and that guy here has variance sigma squared, and there's sigma squared there. Maybe we should add this again here to the slide. So epsilon is a Gaussian which is 0 mean and variance sigma squared. So obviously the variance, as the variance increases, the expected error is going to increase. But for a fixed variance, as the number of samples increase, the expected error is going to decrease. And that decreases for two reasons. One, because the noise term decreases, but also this term decreases. The expected error. Now this is not the answer. This is just the difference from the answer. And so what's going to happen is that as n increases, this whole term is going to go to 0, and this whole term is going to go to 0. So more data. There's no data like more data. This is a good mathematical description of how more data helps mathematically. And then last but not least, you might say, well, what's the best trade-off between bias and variance? Actually, I hope I started the video again. Sorry, let me just check this. Yeah, it's going. Okay, it's recording. I just had a panic attack. Like, did I forget to start the video? Right. So the optimal one. Basically, what we do is we take the derivative of this, set it to equal to 0, solve for the best lambda, the one that minimizes this quantity, and what we get is this. So that's the best trade-off. So life ordinarily is not so good, by the way. You can't ordinarily come up with analytical expressions for all this stuff where you can actually see so clearly the bias and the variance trade-off, and you can find the right regularization parameter that gives you the best trade-off between bias and variance. So life is not ridge regression. But whenever you are doing ridge regression, and there are many cases where ridge regression is still very useful, linear regression is still used all the time in the real world, you can find the right trade-off. You can do all this stuff. Test it out. But besides doing that, the question we might want to ask is, how do we see how well we're doing? So we said, that we've got this learnt model. Maybe we've found the best trade-off coefficient, or maybe we've tried some other trade-off coefficients. But how do we know? Are we really doing as well as we think we are? Well, one way would be to actually look at the overall cost. But if we measure the cost, that's that's not great because we're measuring the cost that we minimize. It's the direct thing that we minimized, and that's always going to be probably small, depending on what lambda is. And for each data set, it's going to be low, and so we're not really seeing how well the overall cost is. The ideal thing would be to actually go back to the probability distribution, the true probability distribution, and somehow compute this thing. And so remember in the overfitting document, we had the accuracy of H, and we also had the accuracy according to some data set of H, right? So this error corresponds to the overall accuracy. You're integrating over and with respect to the overall data. The second bullet point is what we would really like to do. It's mathematically the best thing to do, but it's impossible to do because we don't have the probability distribution, and we can't, even if we did, it would be intractable to compute it. And so what we do instead is we use a validation set. Now, in the write-up I posted, actually, I made a mistake. I used the word evaluation rather than valuation set. The right term is to call this a validation set. It's typically not called an evaluation set. And somehow I just typed evaluation instead of validation. But what we're doing, and actually the document that I updated on the web is using the word validation rather than evaluation. It's either a validation set or sometimes it's called a development set. More common is probably validation. So we use this validation set, DVA, that's non-intersecting with the training set, and we measured how well the model does on this held out set, the set that we didn't train on. And that's a good surrogate for seeing how well we do. It's kind of like, you go to school and you learn stuff. And so you take a test, and a test is kind of like a evaluation set. You take a test in a class, or you do your homework, is what you're doing here. And the grade you get in your class is kind of like a validation set. But then, if you get a good grade, then you go out into the real world, and that's kind of like known as the test set. You actually try it out. And hopefully what you learn in class is representative of what you learn outside of class. So hopefully what you learn in the training set and what you've evaluated with the validation set is a good strategy. Because when you actually have your model and say, hey, I trained on my training set, I did well on my validation set, hopefully that's indicative of your true performance. But the extent to which it's indicative of your true performance corresponds precisely to the extent to which the validation set is of good quality. And if the validation set is too small, or it's sampled from a different distribution, or if it has some other weird properties like idiosyncrasies that are not truly representative of what's in the probability distribution, then it's not going to be a good way of evaluating. So here's a picture that kind of describes all of this stuff. By the way, so we're going to call this be the test data, the validation set. So let's just call it test data for right now. And so here's the ridge estimate. This is the ridge regression estimate. We have blue, which is the training set error, and red, which is the test set error. And we're plotting it for multiple random runs as a function of 1 over lambda, right? So in some sense, lambda is the trade-off coefficient, but you can use lambda to measure the complexity of the resulting learned model, right? Because if it's the case that lambda is very, 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 very big, right? So if lambda is very, very big, you're going to ask for a simple model, right? And so 1 over lambda is going to be very small, which you're going to be right over here. So this is the big lambda, and this is the small lambda. So small lambda allows for there to be a complex model. Big lambda strongly encourages there to be a simple model. And so model complexity you can actually measure in terms of 1 over lambda. It's a way of measuring complexity. And you can see what happens over. Let's just zoom in on this a little bit. Hopefully you can see it on the screen. This is multiple random runs, and you can see that each one of these random runs, it goes down. The training error, remember, so the training error is over here. The training error goes down as a function of the complexity. And this is actually a real run. This is a real run that was run on real data. But what's happening is that the validation set starts by going down, but then it starts going up. Right? So where is the point of overtraining? So I don't know if you remember this figure. Hopefully I can find this. This is exactly analogous to this figure here, where as the complexity goes up, and here we're measuring accuracy rather than error, so it's the same thing but just flipped vertically. What happens is that the training set accuracy goes up, but the validation set accuracy goes up at first, and then it starts going down because we're overtraining. So we have the red region over here, which is the overtraining region, the overfitting region. We have the yellow region over here, which is the underfitting, and then we have the green region, which is the fitting region. So red is overfitting, yellow is underfitting, and green is kind of everything's good. That's exactly what's happening here. So if we were to use the same colors, roughly speaking, yellow would be something like this. Red would be somewhere around here. And green would be here. So this is overfitting, underfitting, and just fitting, properly fitting. And each time you do a random trial, it's going to be different here and there, but notice that this is the trend, right? The training error is going to keep going down. As the complexity increases, you're going to fit the data better and better, but eventually the evaluation, the validation of the test data is going to start going up. All as a function of lambda, which is our trade-off. So that exactly achieves what we wanted. It achieves exactly the thing that we were talking about here, except these are not real pictures. These are just drawings. This is an actual result of multiple runs of machine learning. And you get the same trend. Or the expected trend, I should say. Now, the true error, of course, is what we would like to have. But again, we can't really compute this. This is something that's not possible to compute. But if we could measure that, that would be great. But we can't. So we have to hope that the testing error is representative of the true error, and rely on that, because this is all we can do. Okay, training versus testing versus validation error. So again, here's the ridge estimate. This is the same ridge estimate we saw before. We have the testing error, which is on this data set T. We have the training data set. Now, one thing to note is that this is known as an optimistically biased error, because what this means, going back to this picture here, is that notice that the training accuracy is higher than the evaluation accuracy. We saw these other examples here where it may not, there are some weird cases where the training accuracy might not be as high as the testing accuracy. And those are very weird and improbable situations, but it's certainly possible. In the example that we saw here, we noticed that the training error was below the testing error. And so that's called optimistically biased, because it's biased towards optimism. It's saying that, hey, just looking at the training data set, you're doing better than you really are going to do if you're out in the world. And you have to be careful about that, especially when you're overfitting. I mean, when you're doing a lot of overfitting, you're quite aggressively optimistically biased, because you think you're doing way better than you're really doing. But even when you're underfitting, because that's the objective that you're minimizing, on average, you're doing better in training than you are in testing. And this is the typical case. The optimistically biased case is the probable one. And then this is the training error. The reason why, of course, is that you're minimizing the training error. And then this is the true error again. This is the thing that you wish you could do, but you can't. You sort of look wistfully at your equations, wishing that you could minimize that thing, but you can't, actually. Unless you're in an extremely contrived example. Actually, one of the things you might say, like, what's the use of actually putting this equation down? Does anyone have that question? If we can't do it, why do we care about it? Oftentimes what you can do is you can debug machine learning systems. Like you build up your machine learning system, but you can come up with, let's say, assume the data is Gaussian, and then assume this is the true probability distribution, and then you sample from that Gaussian, and that becomes your training data, and then you use your machine learning algorithm on the sampled Gaussian, but you know the true answer. You know theta star because you use theta star to generate the data, and then you look at your machine learning system and see how close to theta star was your learned theta. And so, and then you can actually look at this area. You can actually integrate with respect to the probability being a Gaussian, because you know that the sample data that you generated was Gaussian. And so that equation at the bottom isn't as impossible to achieve in the contrived setting as it is in the real world. Now, why would you do this? Again, it's for debugging, because debugging machine learning systems is tricky. It involves a lot of skill that's different than debugging regular programs. I mean, you can use your debugger, you have no seg faults, have no overrun errors, and everything works perfectly, and you run lint on it, and you run, memory is being decalculated, and there's no memory leaks, and everything looks perfect. And in fact, you've got huge and serious bugs. So it's harder. There's mathematical bugs that don't show up using normal programming, and you will experience them in your homework. You will find bugs. It won't work. You're going to be frustrated. You're going to post on Canvas, and you're going to say, I tried this, and I get no seg faults, but it completely diverges, and I don't learn. And these guys and me will help you with this, right? That's our job, to help you figure stuff out, right? Figure out how to debug machine learning systems. And that's why there's a big component of this class which is hands-on. Okay, so the last thing I want to say about rich regression is this idea of the regularization path. So one of the things you can actually look at, so remember we said that this plot might look complicated, but it's actually not. So theta, remember, is a vector. We have theta, which is theta 1, theta 2, theta 3, ... to theta m. So you have m different, each vector theta is a scalar number. So it's a set of scalar numbers. And so this is a plot from the Hasty Tibshirani Friedman book, which is one of our recommended reading books. And what they did here is they plotted the value of theta. So this would be, we could call this maybe theta 1, and theta 2, and theta 3, theta 4, theta 5, up down to say theta m. Now, they used names for the thetas because this was a particular problem where the thetas were corresponding to very specific input variables. Because remember, what we're doing is theta transpose times x, and so it's a dot product, right? What we're doing is we're summing up the product of a theta with its corresponding scalar element in x. And so we can give names to the thetas in certain cases. But ignore the names for the moment and just look at just assume that these guys are the different values of theta. And so on the x-axis, what we're doing is measuring complexity again. So more complexity as we move to the right. And you can kind of think this as like approximately equal to 1 over lambda. We'll talk about this in a minute. But it's as complexity increases. And it's a particular way of measuring complexity where 0 means no complexity. Because obviously if you set lambda to be infinity, it's hard to plot that. But this would be 0. And you can see that when you're saying that, when you're allowing the model to be very complex, you get lots of large magnitude coefficients. Like as the complexity increases, or as lambda shrinks, as lambda itself gets smaller and smaller, the resulting learnt theta value has the greatest magnitude values. Like this one is bigger than all of the others, and maybe these ones are big but negative. But as lambda gets larger and larger and larger, and so that the complexity of the resulting learnt model gets less and less, the resulting coefficients shrinks. And so they shrink down from their largest value until eventually they all hit 0 at about the same point. They all hit 0 at the same point. And then you can kind of zoom in. Let's see if I can zoom in. How much I can zoom in. But they all sort of eventually collapse to 0. And they collapse to 0 at the point at which lambda gets very, very large. Now, in this particular plot, what we're measuring is not 1 over lambda. We're not measuring complexity of 1 over lambda. What we're measuring is actually what's called the effective degrees of freedom. And the effective degrees of freedom is this quantity here. It's df, or degrees of freedom as a function of lambda. And what it's doing is it's summing up for I is equal to 1, for j is equal to 1 to m, dj squared divided by dj squared plus lambda. So you can see that it's kind of similar to 1 over lambda, in the sense that as lambda gets big, it goes to 0, and as lambda gets small, it reaches its maximum value. And its maximum value in this particular case corresponds to m. Right? So df, 0, when lambda is infinity, then of course it's going to be 0. And when lambda is 0, when there's no complexity penalty, you get the maximum number of degrees of freedom, which is m. And it's kind of useful because, when you have lambda itself as a parameter, or 1 over lambda as a way of measuring complexity, the units are not so great, right? Because, when you set lambda equal to 0, you get infinity, or you get these really large values. But, when you have no penalty at all, you have m coefficients, right? So there's m different scalar values for lambda, right? Theta, right? Theta is a length m vector, and so there's m possible values. There's m scalars in theta, and so that's the greatest number of degrees of freedom you have in your machine learning problem. And it should be the case that as you put more and more complexity on it, the effective number of degrees of freedom should decrease. But it's not necessarily an integer; it can kind of sort of fractionally decrease. And so the effective degrees of freedom does this. And if you take the, what are the Ds? The Ds turn out to be the eigenvalues or the singular values of this matrix X, of the design matrix. And if you compute the singular values of the design matrix and use it in this quantity here, that actually gives you something that can be interpreted as the effective degrees of freedom, which is a number between 0 and m. And therefore it has this nice interpretation. So, right, so there you go. So now this is a picture we're going to come back to. We're going to talk about the lasso, which is another form of regularization. So remember we said there's lots of different ways of measuring complexity. The ridge measures it by taking this squared 2 norm. And I emphasize that all of these coefficients collapse to 0 at the same point. It's kind of like all or nothing. They all go to 0 at this point when df is equal to 0. Is that what we want? We'll talk about it in the context of lasso. Okay, so that is the end of the discussion for ridge, and I want to, question. So you're learning to anticipate my questions.
Again, basically how you design the lambda.
How you design the lambda?
Yeah.
So if you're doing ridge regression, one way of doing it would be to use this formula, wherever it went. This guy right here. However, we're going to learn another strategy in the next section.
But do you know all this, like the m and the sigma? Do you know in advance?
Sigma you don't know necessarily.
Yeah.
Right? Sigma you don't. So you know m, you know n, but you don't know sigma. So you'd have to somehow guess at sigma.
Okay.
Right? And so that's it's kind of like a chicken and egg problem. If you don't know sigma, that's one of the reasons why what we're going to be talking about is cross-validation. This thing here, which we're about to talk about, will work even when you don't know sigma. That's a good point, and I should have emphasized that. So, need to know sigma to get lambda star. You need to know the noise, and if you don't know the noise, you're kind of out of luck. Great question. Any other questions?
What's the advantages or disadvantages of reducing the complexity of the model after the fact, like after you train?
The advantages of it are that you don't need the data, and the disadvantages of it are that you don't need the data. So the advantage of it is that once you've got the model, maybe you can sort of look at the coefficients and just do some thresholding and say, oh, those thetas are so small, I can just set them to 0 and prune off anything that's really small. But at the same time, you're kind of like not involving the complexity reduction, you're not involving the data in the complexity reduction until after the fact. And so maybe during the process, you want to be able to see the effect of, like maybe there's a real need for having that one small theta. And as soon as we decrease that, something else goes haywire. And if we have the data and can keep optimizing, we can see the effect of doing that, at least on the training data. But there's also other practical advantages, like maybe you don't need the data, and if you ship the model and then you don't have the data, or maybe there's a privacy issues associated with the data, and you don't want to ship the data to your customer or something, then this model's out there and they want to prune it themselves, or they want to simplify it themselves without actually having access to the data. So that's a practical advantage to doing it after the fact. But most of the time, most regularization strategies try to simplify the model while the data is still present.
On that plot that you were talking about, the very last one.
Sorry, let me say one more thing about this. I mean, here's another example. I mean, this is an example. It's like, let's say that I just thought of another good reason for doing it while the data is present. Let's say that this is your space. So this is your X space, and that's everything that's there. So one possible data set might only live here, right? It's really like this is the set of things that could be represented, and all of your data lives here, right? And if you have the data, you can see that any of the coefficients that are kind of far away, or that affect what happens far away from the data, you can say, okay, well, I don't really care about those values of theta, or that part of my model. This is just more general. It's like you want to try to prune your model or simplify your model after you're done with training. So during training, you know that you have no data except for this region here. And so anything that affects the response of your model to stuff that's away from your data is possible to do, right? But now, okay, so now let's say you've got this model and you want to somehow simplify it, and you don't have the data. And so you don't have the data, so you don't know that your data was really concentrated in this region. And so what happens is that you prune your model, or you do something to simplify your model, and what that does is it suddenly changes completely the way that your model responds right where you need it to not change. But it doesn't change where the model responds. It doesn't change the model where you need it, where you don't care how it responds. Like you might not care what your model does in this region of X, in this region of X, and this region of X. You don't care because you never see data there. It's kind of similar to when you're doing face recognition. What should your model do when you have a random dot pattern? It's not a face, it's nowhere close to a face. Maybe you don't care what your model does in that case. I mean, that's actually maybe not a good example, because I think maybe in that case you do care what your model does. But there are some examples of machine learning where you're so certain you will never see data of that form. You don't care how your model responds out of the regime where you have data, where you're likely to see stuff. But if you don't have the data, you don't know what you're simplifying. Are you simplifying it here? But if you're doing it while you're training, you can say, okay, well, I don't care what my model does in this region. What I care what my model does is in this region. And so therefore it's better to have the data. It's better to be doing the complexity reduction while the data is present, during the learning time in general. Yeah, you had a question.
Oh, yeah, on that last plot.
Which one? This one here?
The very last slide.
Oh, the one before this one, yeah. This one.
You were saying earlier that you can kind of relate the lambda to the maximum value of theta. Is this kind of saying the same thing as the lambda gets bigger than the theta gets smaller? And can you?
It's kind of saying the same thing, except it's kind of like the range. You know, the range of the x-axis is kind of normalized. Like, you know, how many coefficients are there in this picture? There's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 coefficients, right? So the effective degrees of freedom, the maximum, since the effective maximum degrees of freedom is m, and in this case there's m coefficients. This is the case here when lambda is equal to 0, right? If you plotted 1 over lambda, like if you had this kind of plot, 1 over lambda, you would see the same kind of thing, except with lambda is equal to 0, it would be way off at infinity, and sort of like the x-axis would be really far away over there. I mean, so and how would you plot this? I mean, this point here would be way off the axis, and so what this does is it says, okay, well, since the effective degree of freedom can never be more than m, this is the case when lambda is equal to 0, right? Because when you set lambda is equal to 0 here, it's just the sum of m1s, right, which is m. So that's the difference between this. And so generally this, like, even if you didn't use d, I mean, one you could just wing it and just do something like the sum for I is equal to 1 to m of 1 over 1 plus lambda, right? And that is sort of a way of measuring complexity that may be a little bit better than 1 over lambda. Right? I mean, it's better to do this with with singular values, but this would be another way of using this. This would be like approximately equal to df of lambda. It's just a different way of doing the x-axis rather than 1 over lambda. Because in this other plot here, notice this was 1 over lambda. So in order to get the point where df is m, it would be way off to the right. For this plot, it's okay because we can already see that we're overfitting. Does that answer your question? Okay. So that's ridge. Now, what happens? What's another way of doing regularization? How do we, for example, how do we find lambda when we don't have the noise, or maybe we don't have a nice ridge regression problem? And generally, the way to do it is to do this notion that's called cross-validation. We have a training data set D, but we don't have the luxury to sample multiple data sets, and we don't have the ability to go back to P of x comma y and sample more data from P of x comma y. All we have is our training data set D. Right? So what we'll typically do is we'll take the data set, like this is all of the data we have. Like maybe we'll buy a data set, or we'll commission a data set, or we'll download a data set from Kaggle or from somewhere, and then we have to do something with our data set to mimic having a training set and a validation set. And so one way of doing it is to arbitrarily split the data set into a training set and a validation set. And the training set is used for training, and the validation set is used for validation. But then you might ask, well, what if that's bad? What if we've done a bad split? How do we know how to do a good split? Well, one way of avoiding that is before we do that, so we can use that split to decide the lambda. I got a little bit ahead of myself. Let's not worry about if this is bad for a second. So once we've got this split, we've got a training set and a validation set, we can use that to decide lambda. So how? We go back to this kind of plot, and we just train, so we train with different values of lambda, and we know that as lambda decreases, the model is going to get more and more complex. But now we've got a validation set, and so we can measure the model on the validation set, which is this part, and it should be going down. But then at some point, what's going to happen, likely, is that when lambda gets too small, the validation error is going to start going up. So this point, the low point, the minimum of this curve here, we have to do multiple runs. So we have to train many times. But as we keep training and we keep evaluating on the validation set, eventually there's going to be some point which is the minimum value, and that's going to be 1 over lambda star. And that gives us lambda. Or we could do the same thing with the effective degrees of freedom. Okay, does that make sense? So this would answer your question of like, how do you choose lambda? We use a validation set, and we do it in a way that the validation set is small. But then you might ask, well, the question that I asked earlier is, what if it's the case that you've chosen a poor validation set? Like, what if it's the case that you're doing digit classification and you're trying to classify the digits from an image into the digits 0 through 9, and you put all digits 9 over here, and these are all of the digits 0 through 8. So you're learning how to classify digits 0 through 8, but you're testing just with digits 9. So chances are you're going to do terribly, right? Because you've never in your training set seen a 9 digit, and all you've seen are the digits 0 through 8. And so your model's going to learn that there is no such thing as the digit 9. Digit 9 doesn't exist. And it will only decide, and anytime it sees a 9, it'll say, well, that must be a 0 through 8. And it'll find whatever, based on whatever parameters the model are, that whatever digit looks closest to that particular digit 9, it will choose one of the first, it will choose digits 0 through 8. So it's a poor split, right? So what do we do? Well, we can split multiple ways. And so here's an example of taking all of our data and splitting it into 5 different sets. So we have split 1, 2, 3, 4, and 5. And in each case, we choose a different validation set and use the rest for training. So here's this validation set, and this becomes training, and this is the validation set, and this becomes training, and so on. Down to the last example where this is the validation set and this is the training. And so that gives us 5 different splits. So how would we then use that to choose lambda? Well, we try all 5 of them, and we see how well the validation sets do for each value of lambda, and take an average of the validation sets and choose the lambda that gives us the lowest error on average over all 5 validation sets. Right, this is something that's known as 5-fold cross-validation, and it's very common. It's used all the time, and the proportions, by the way, of 5. This is 20% and this is 80%. Like we typically will take 80% of the data for training, and 20% of the data for validation, and then do that 5 times. Now, there's many more than 5 ways of choosing 80-20, and you could do even better. Rather than choosing this 5 times, you could just take a random subset of 80% and the remainder 20%, and then do that 1,000 times, and you'd have 1,000 training and validation splits, and then you'd average, rather than over 5 numbers, you'd average over 1,000 numbers, and then choose but that becomes expensive, right? The more you do that, the more accurate your estimate becomes, so the better you become, because if you're doing it on average, chances are you're going to do well. You're going to average out all of these bad cases. But at the same time, it becomes computationally costly. And so there's the trade-off between, well, how much time do you want to spend finding the right lambda? Maybe 5 is enough. And in general, how many times you do it is called k-fold cross-validation. And that's what we just talked about. And that's really important, k-fold cross-validation. You hear that term all the time. Now there's another type of cross-validation, which is called leave one out cross-validation. And what leave one out cross-validation does is the following. It says, well, let me actually pause. Are there any questions about k-fold cross-validation? Yeah, question. Oh, sorry.
Knowing how well we do in the validation set, is there like some sort of a mathematical formula or something that would allow us to decipher that portion?
No, it's pretty much empirical. Now there are some results, some mathematical results that say if you do cross-validation, you can sometimes, in certain cases, if certain circumstances are true, prove that that's better, that you'll get a good lambda. But in general, there's no like single analytic formula like we saw in the ridge regression case that says, here is the best lambda. That generally doesn't happen.
So we just keep changing the lambda until the validation does better.
That's right. You would say, for example, for lambda is equal to 0 up to some threshold. Or if you're using this effective degrees of freedom, that's kind of nicer because it gives you a range from 0 to m. And you could have changed the effective degrees of freedom from 0 to m, and where m is no regularization at all, and 0 is infinite regularization or something, and then you could choose like 100 steps between the, and try 100 different lambdas.
Is there a trade-off between the size of your validation set with respect to like all the data and how many folds you do? Like, do you have like a smaller validation set and just do all the folds?
Yeah, there is, and in fact, that's getting into exactly what Leave went out cross-validation. So generally, like, what's good about doing if you say do 90-10 or 95-5 or 99-1, I mean, so you have there's a danger with this, right? Because what can happen is as you have less and less data to train on, so what happens? The chance of potentially, I mean, it's kind of like you're cursed no matter what you do. There's danger lurks in all corners of machine learning. As you use less and less data to train on, what's going to happen in your bias and variance sense? You're going to overfit. Your variance is going to go up, right? So your variance is going to go up, and your estimate, if you like, let's say you want to have a good validation set. So you set your validation set size to be big. So then your training set size is small. So that means that every single data set you're going to learn the idiosyncrasies of that small data set, which means that your learned model is going to be different, which means that you're going to perform very differently on your nice big validation set. But at the same time, if your validation set is too small, then that's not representative of the true distribution, right? So you might actually have a large data set, you have smaller variance because you have a larger training data set, but your validation, the way you evaluate is not representative. So it's kind of that itself is a trade-off. And then of course the number of splits. How many splits you do. I mean, you can do it in the way this figure does. In which case you choose successive sets of 20. But or you could do random subsets. But as a rule of thumb, most people do 80-20. And there's also the computational consideration, and that's also a trade-off because you could do more at more computational cost, more time, and more money, and more energy. All of those things cost more in one way or another. But 80-20 seems to be universally agreed upon. Although maybe someday that will be revisited. Leave one. Did you had another question?
So for each one of the split, are they all the size of the all data, or they are like 1/5 the size of the data?
Well, in this case, it's an 80-20, so it's 80%, 20%. So the training data is 4/5, and the validation set is 1/5.
I mean, for each one of the 5 splits, so are they all like the same size of the all data, just split it in different ways?
Yes.
Okay, and we use this just to find the lambda, right? And after you find lambda, you do the training all over again?
Yes. Yeah, that's typically what you do. Is like once you've found the right lambda, then you can go back in all of the data, use that resulting lambda that you found, and that then becomes the model that you ship, right? Because the final lambda, now it's not perfect, right? Because the lambda that you found with size 80% of the data might not be the best lambda that you use with 100% of your data. So even there, you're not, like if let's say you had 100 samples, and you've learned a great lambda that works with 80 samples, and then you use that same lambda to learn with 100 samples. That's not necessarily the same lambda that you would learn if you had 125 samples to begin with and did 5-fold cross-validation with 100 sample training sets and 25 sample test sets or evaluation sets. So again, you're kind of no matter what you do, you're wrong in machine learning. The question is, how do you be least wrong? And the way to be least wrong is to learn about all of this stuff and to be wary of it and to think about it and to always be skeptical of everything that you're doing with respect to bias and variance, overfitting and underfitting, the complexity cost trade-off parameter, and explore the space and think, and then you can get it to work. Okay, so leave one out. Sorry, was there any other question on this slide? Yeah.
So you never mentioned theta in these training things. Do you not look at the theta?
No, you do. You look at theta. These are the data sets that are used to learn theta. Like theta are the parameters of the model that you're learning. But the question is, what data do you use to learn theta? And so here is, like, we would learn. In this case, we'd learn, like here, we'd learn 5 different thetas. We'd learn a theta for this training set, and we'd learn a theta for this training set, and we'd learn a theta for this training set, and so on and so forth. Right? So each one of those training sets, we'd learn a different theta. But then we'd see how well does that learned model do. The first theta, we would test it on this set. And the second theta, we test it on this set. In each case, the training and the validation set are disjoint. Right? There's no overlap, and that's actually a huge. That's a worry. It's like training on the validation set is a pitfall. If this wasn't disjoint, like if this wasn't true, then you'd be in trouble, right? Because then you would get into this optimistically biased situation again, which is you'd make your model look better than it really is, and you generally don't want to do that. So.
So then, do you also average all the 5 thetas?
You could average the 5 thetas. I mean, sometimes it makes sense to average the 5 thetas. I mean, one way of doing it is, if things make sense to linearly aggregate things in terms of the parameters, sure, you could try that. And I think in linear regression, it probably would work fine. What you can do instead is just go ahead and do one more training on all of the data. Right? But yeah, that's a good point. You could average the 5 thetas. Now, in the case of other kinds of models, for nonlinear models or deep models, things wouldn't necessarily. I mean, how would you combine these different models? Maybe you shouldn't. I mean, there's other forms of combining models where you don't average the coefficients, but you average the outputs of the models. Right? And you say, well, don't average the parameters, but average the predictions. Like there's a technique called boosting, which we will talk about, which does that kind of thing. It's like a weighted average of the outputs, not necessarily the models themselves. And there's lots of ways of taking different models and averaging their outputs. We're going to talk about bagging, bootstrap aggregating, which is another form of that. We will talk about that in the next lecture or two. And that means you have to keep each of the models around and keep them distinct. You don't get one model; you get lots of models. You can combine them together afterwards, after they're all learned. Because that way you can sort of guarantee. And in fact, there's lots of ways of averaging models. Sometimes you can actually put them into an election and have them vote on the right. Like every model becomes a voter, and you have a vote on what the right decision is. And that often works really well. I mean, democracy works well in machine learning when you have a vote. It's pretty neat when you see it. You have each of these models which themselves don't do so well, but if you look at the majority works much better than any one of the individuals. That happens a lot. Okay, so leave one out cross-validation is essentially kind of like cross-validation, but where you only leave one out. So you have a data set D, and let's say that D is one of the samples. And so what the ridge regression estimate would be is basically you estimate a model on all of the data except for this one held out sample D. And so you have the ridge estimate, which is theta, it's based on lambda, it's ridge, it's an estimate, it's based on the data except for, so this notation here, let me just zoom in on that for a second. So this notation here, oh, that's too big. So that notation means all of the data except for this particular sample. Except for this particular sample. It's kind of like set subtractions, like D minus lowercase d. And so in the ridge estimate over here, you take the design matrix which is all the samples except for D, which is the same thing here, and you get an estimate here. And similarly, you take the y vector, and you take all the samples except for D, and that gives you this estimate. And so that basically means this matrix here, that's rather than an n by m matrix, it's an n minus 1 by m matrix for each D in the data set. Because you're leaving one out. Each time you leave one out, you have one fewer sample, and that's n minus 1. But then you can average over all n of those estimates, right? So you can actually have an error. So here's the overall estimate. So you estimate this model, leaving out the ith sample, and you see how good that ith model is at predicting the one sample that you haven't trained on. And then you take the square difference and you take the average, and that becomes the leave one out error. So it's like n-fold cross-validation, where the cross-validation set is only size 1. The validation set is size 1. So interestingly enough, it's for estimating the true expected prediction error. It's sort of like almost unbiased, meaning it's very close to the true expected prediction error. So you can get a good idea of how good the error is. So it's pretty good. But at the same time, even though it's got low bias, it's got high variance. And the reason why it has high variance is because every time you're training on a data set that's almost like the original data set. You're only leaving one out. So when you think of how does it respond to different data sets, the leave one out estimate, if you have one data set and you average over n models, you're going to get an average. But then if you have a different data set, you're going to kind of get the same kind of variance you're going to get as if you used all of that data set to begin with. And the reason why is that each one of these estimates, each one of these leave one out estimates, is not that different from using all of the data. Just because you're only leaving one out rather than leaving lots out. And so therefore you have the same variance as the original. And of course it's very expensive because, like, let's say you've got 1 million samples and you leave one out. So nobody actually does this in practice. I mean, you're going to do 1 million models and average over 1 million models. If you train 1 million deep models, that's going to take forever. So you can't really do it. So generally what you do is n-fold cross-validation. So k-fold cross-validation, it partitions. It basically divides the data into k non-intersecting blocks. And the non-intersecting blocks is critical. And you try to make them balanced so that they're all about the same size. And that's what this picture is here. This is an example of 5-fold cross-validation. Because notice that this and this don't overlap. This doesn't overlap with this. This doesn't overlap with this. And this doesn't overlap with this, and so on and so forth, right? So there's no intersection, and that basically comes from this property here. So that DI, the intersection of DI and DJ is the empty set for all IJ. Yeah, question?
Yeah, since like the leave one out was just leaving one of these data sets out, is there any advantage to maybe using different than 80, doing k-fold, but doing different percentages on the different sets? So it's maybe not 80-20 on all of the k-fold set that you do.
Again, it's the same kind of bias variance trade-off, right? You think about it in terms of bias and variance, then as k gets big, right? So let's say k gets big. So like in this case, when k is equal to 5, it's 80-20, right? When k is equal to 20, it's 95-5.
No, I meant like for these 5, right? Like there's use a different percentage on each of these 5. Like maybe the first one is 80-20, the next one is going to be 90-10.
Oh, I see. Yeah. So yes. So here's an advantage. So it would require a bit of analysis, but this is what you could do. So the thing I was saying before, let's just think about that for a second. So when k is very large, right, then you have large training sets and small test sets, right? So the large training sets mean that each estimate is going to have relatively low variance, right? Because the training sets are high, right? But possibly high bias. Whereas when you have a low K, right, then the training sets are going to be small, and so each estimate of the model is going to have high variance and low bias. So one of the things you can do by using different values of K as you go along is see whether indeed these different models on different size training sets do differ in meaningful ways. Because like just because there's a tendency to have high variance doesn't mean you necessarily do have high variance. The data could be in a particular way that you do learn the model. It's all relative. It's all it's saying is that the variance, as you have less and less data, you have more and more variance, right? And as you have more and more data, you have less and less variance, and higher bias, right? So, the bigger the data set, for a given model complexity. This is fixing the model complexity, because there's two ways of controlling bias and variance, right? One way is model complexity, the other is data size. You can, if you have a huge data set, you can deal with a complex model. If you have a limited data set, you should try to regularize a lot, right? To account for the fact that you don't have a big data set. You want to prefer simplicity. You want to have the simplest thing that fits the data. But if you have a lot of data, there are more complicated things that you're willing to accept. So what you can do different Ks with is actually look at and compare the predictions for each of these different models. And if it's the case that they all agree with each other, then maybe you can find the best K. By trying different Ks. That would require a lot of work, right? So you'd have to spend a lot of time trying to find the right lambda by looking at different Ks. But
my ignorance here. In general, like what sizes of data sets are you generally talking about? And like what is N?
Well, it could. I mean, in your homework you will be learning that. But I mean, N could be as small as a few hundred, or it could be as large as hundreds of trillions. I mean, it's generally. I mean, in machine learning today, people. I mean, like some of the self-driving car data sets are massive. I mean, there's massive amounts, petabytes of data. Whereas other data sets, like when you're doing simple, linear regression in the lab in Python, you can get by with a few hundred samples, or even tens of samples. You can learn with tens of samples. And the other thing, of course, that matters is M, right? So like as M gets larger, you need to have. We're going to learn about this. That's the curse of dimensionality. As M gets larger, you need to have exponentially larger M. So that's why you want to have M as small as possible in general, if you can deal with it. Yeah, I mean, so the practical side of things, and you learn in the homework. In the homework, you will be exploring different size data sets, different M's, and so on and so forth. So this is the k-fold error. So unlike the leave one out error, the k-fold error has the cross-validation error has lower variance, but higher bias, right? So because I mean, again, this is the idea. It's like you're using only a k minus 1 over k, which is less than one fraction of the data. And if it's the case that just by using that fraction less than one of the amount of data, if that significantly increases the bias, that could also significantly increase the error. Because remember, the overall error, is a combination of the variance plus bias squared. And which is the dominant part of that error? If you're already in the regime where using all of the data is giving you a high bias, then decreasing the data is going to make that bias even worse. The variance might already be small. So it depends where you are on that curve. So like I said, there's no one answer to this. The answer is to be aware that you're somewhere on this x-axis. And then you explore around to find out where you are. And then you make decisions based on that. And that's the only way to do it. I mean, especially when you have new data sets. Oftentimes, like when you're doing things in school, like we're in school now, everything, a lot of the data sets that you're using, someone else has used. But you have to pretend like nobody else has used it before, because when you really when you go back to wherever you work, and I always say this, and like your manager says, take this machine. Maybe you're doing this class for self-actualization. You just want to learn something new. Or maybe it's the case that your manager has asked you to take a machine learning class because they want you to apply it for some problem that you have at your job. Your manager says, great, you took this machine learning class. Here's this big data set. Get it works. Get data. You're now our our lead data scientist in our company. Please solve this problem for me. And they throw this big ton of data at you, and now suddenly you need to solve it. You're going to have to explore this bias variance trade-off by yourself, because nobody else will have done it for you. So, yeah. And of course, your manager doesn't know anything, right, about data science, right? Your manager is completely ignorant and just expects it to suddenly start working because they read it in The Economist that AI is the solution to everything, right? So. Okay, so I think it's worthwhile to take another short break. But I have a feeling that people want a break. My read of the room is that people want a break. Now, if I'm wrong, then all raise your hand and say, no, let's keep going and not take a break. Okay, so I think I'm reading you guys correctly. Let's take a short break, not a long one, and come back and do multi-class. Let's continue on. Okay, I see everyone here is a real dedicated machine learning researcher, so this is great. So we got 45 minutes to go. So what we're going to talk about for the rest of today's class is multi-class classification. So we saw that logistic regression is good for binary classification, and a binary classification means that what you're trying to do is you're trying to decide between one of two options. And ideally, you'd like to make a prediction or maybe come up with a probability distribution over those two options. And we saw that the logistic function and logistic regression worked well for that and made a lot of sense for it. Although we can use other forms of sigmoid functions as well if we want. This is something else. And we saw the gradient of logistic had these nice properties and so on and so forth, which was very nice. Now, what about multi-class classification? So, first of all, what is multi-class classification? So multi-class classification basically means that we want to decide between more than two possible outcomes. Like, for example, maybe we want to decide between three possible outcomes. So here on the left is a typical binary classification problem. And so we're in two-dimensional coordinate space. And over here are the reds, and over here are the blues. And we want to decide a classification line of some sort, or separator, that separates out the reds from the blues. So it's two classes. It's a binary classification problem. But you can imagine just as well that maybe there are problems where we want to decide between more than two problems. Like maybe you want to go to the store and you want to decide what kind of fruit to buy. Should I buy, oranges or apples or mangoes? Or or maybe I want to decide between. You want to do face recognition of some sort, and you want to decide between one of a number of people, and the number of people might be very large. It might be thousands or tens of thousands or millions of people. So in some sense, that's a multi-class classification problem, because it's not three classes, it's a million classes, where the input is a picture of the person, and the output is one of these million classes, which is which person it is. So there are many, many problems in machine learning that are inherently multi-class, and binary classification doesn't suffice. So the general idea is that what you're trying to do, it's an associative memory, as we talked about. You're trying to map from an input, and the input in this particular, my iPad is freezing. Hold on. Yikes. What is this doing? Okay, so hold on. That works. That works. This works. Why is that not working? How about this? Let's try that. Okay. Okay, so let's do that one. So we're trying to map from an input, which is an m-dimensional vector, to this, which is a positive integer. So z plus is the set of, so it could be 2 or 3 or 4, whatever. I mean, now our tools at this point consist of linear regression and logistic regression, but that's not enough to do multi-class. I mean, if our problem is multi-class, then it's not going to work. Now, one of the things we could do is we could like separate the classes into two groups. Like in this particular case, we could sort of do binary encoding. Like here we have 3 classes, and so we could turn this into 2 binary classification problems, right? But that would give us 4 classes. And in fact, if we always turn it into multiple binary classification problems, everything has to be a power of 2 number of classes, right? It would have to be either 2, 4, and 8, and 16, and so on and so forth. The problem is, why should necessarily the number of classes you're trying to distinguish between be a power of 2? And it might be quite off. Like, what if it's the case that you want to do 65 classes, and then you say, okay, well now I guess I need to do 7 binary classifiers, which gives you 128 classes, right? Which is not good. So what are you going to do with those extra 63 classes? You can classify 65 of them, but you have 63 left over. So what are you going to do with them? Now, fortunately, logistic regression can in fact be generalized to multi-class classification in a very natural way. So before we do that, let's sort of examine and look at logistic regression in a slightly different way, where we have twice the number of parameters. Okay, so what does that mean? So logistic regression, remember, had this form where we have h theta of x, and we wrote this as g, which is g is the logistic function of theta transpose times x, and here's the actual expression. But let's write it in this strange way, where we're setting theta to be equal to theta 1 minus theta 2. So theta 1 and theta 2 are 2 vectors such that their difference is equal to theta. And so what we're doing is we're substituting theta here for theta 1 minus theta 2 here. And once we do that, we can actually write it in this form. So we can multiply and divide by exp of theta 1 transpose times x, and we get that this expression here is equal to this expression. Now this is true. This is something that's true for any value of theta 1 and theta 2. Right? It doesn't matter. It's still the same, as long as it's the case that the difference is equal to theta. We can pick any theta 1 and theta 2 such that this is true and write it in this way. So there's a lot of flexibility here. But let's just go with it for a minute. So then what it says is to say, okay, well, it's binary classification, and we can see that we would choose class 1 if theta 1 transpose x is greater than theta 2 transpose x. And the reason why is because if theta 1 transpose x is greater than theta 2 transpose x, then this is going to be the posterior probability. The probability of the softmax of the logistic output is going to be greater than, say, 0.5, which would correspond to class 1. So this is the effective decision rule that's identical to, say, choose the class that has highest probability if we needed to make a decision. Because remember, in logistic regression, we can interpret the output as the probability of that being the class. And otherwise, if this inequality is not true, then we would choose the other class. Now, one of the things we've done is we've said, okay, basically we've turned this into a simple linear threshold decision rule, right? We've basically said we have 2 linear functions on x. We have a linear function on x associated with class 1, a linear function on x associated with class 2, and we make a classification decision whichever linear function has the highest value, right? Now, we've not really done anything, but at the same time, when you're doing binary classification, there is a redundancy in the probabilities as well, just in the same sense like probability of heads is equal to 1 minus the probability of tails. You don't need to store, if you know that the probability of a biased coin, the probability of heads is 0.6, you already know automatically that the probability of tails is 0.4, because you know that there's a constraint that the sum of the probabilities sum to 1. So this is kind of like a non-probabilistic way of expressing the same kind of redundancy that exists amongst probabilities. If you have a probability distribution over L possible outcomes, you only need to know the probabilities over L minus 1 of those outcomes before you know the last one, the Lth one. And so this kind of redundancy makes sense given that, we have the same kind of redundancy for the output of the logistic function. I'm going to skip over that part because I don't think it's relevant to the current conversation. So, so how do we generalize this? So how do we use this stuff over here, this slide, which is really this part? How do we use this to come up with a generalization of logistic regression that applies to more than two classes? Well, we're going to use this decomposition. And we've got a data set, just like before. X is n-dimensional vectors, just like before. But now the output, the label, the thing that we're trying to predict is an integer from 1 to L. So it's L is the number of classes. Right? So if we're, for example, trying to do face recognition, then X is a representation of the image, and L is the number of people we're trying to recognize based on their face. If we're trying to do speech recognition, then X is an input speech waveform, and L is the set of possible sentences that you might say. So before L was 2, and now L is greater than or equal to 2. And the other thing I want to mention is that we're going to use this inner product notation. This is a very standard notation here. Let's just zoom in on it just so that you see it. This notation. So when we use these left and right angle brackets, this is known as the inner product, and it's really just the dot product. But we're going to be introducing this notation and using this going forward. So whenever we see this on the left, it really means the same thing on the right, dot product. So in the binary case, when we said decide class 1 if theta 1 transpose x is greater than theta 2 transpose x. Right? So, and otherwise, decide class 2. Right? So if this guy, that's a dot product. If that dot product is bigger than this dot product, then we decide class 1. So we could say decision on x is equal to the argmax over j in 1 and 2. It's the argument of the maximum of theta j transpose x. We just compute all these dot products and find the j that maximizes, that has the highest dot product. Because each dot product has an index, right? And that's exactly what this is saying here. So what if we did the same thing, but rather than having only two vectors, j is in 1 to 2, what if we said something like, we cross this off and we say, let's say that j is now in 1 to up to L. So we have L vectors, L separate theta vectors. So that kind of gives us a way of doing multi-class classification. It basically means for every class, for every outcome, for everything we're trying to recognize, we need to have a separate theta vector. Very much like the sort of expanded logistic regression, where we have a theta vector for the zeros and a theta vectors for the ones. So now we have L classes, and so we have a theta vector for each of the L classes. So for each of the L classes, we have parameters, theta vectors, theta j. Now these are known as theta linear discriminant functions. So these are discriminant functions. So discriminant because they discriminate between one class from the next. They make a distinction between one class and the other class. So they're discriminant functions. And the reason why they're linear is because each one of them is itself linear. It's just a dot product. So it's linear in the parameters, and in this case it's linear in the features. So, and this is a very classic concept in machine learning, linear discriminant functions that are still used today. Now, logistic regression becomes this, right? Logistic regression is when we have two classes, and what logistic regression is essentially a formula that involves these linear discriminant functions, except that there's only there's 1 in the numerator. This would be, for example, the probability of class 1. And in the numerator, we sum over the exp of each of the linear discriminant evaluations for all the other classes. So the way that we can generalize this is, instead of having only 2 in the denominator, we have L in the denominator. We sum up over all of them. So we sum for j is equal to 1 to L of exp of the jth linear discriminant function. And that becomes, so H here, we said that this is equal to the probability of C1 given X, right? Where C1, it could either be C1, class 1, or class 2. But now, notice that the ith discriminant function is in the numerator, so that should give us the probability of the ith one. And this is for I in 1 to L. So that's it. That's multi-class logistic regression. First of all, the important thing to see is, do you see how it immediately generalizes logistic regression? Rather than 2 in the denominator here, we have L in the denominator. And rather than only 2 probabilities, we have only L probabilities. We have L probabilities. Now, you'd expect there should be some redundancy here too, because in the case of linear regression, we said that, well, we can simplify this and have only 1 theta vector. Similarly, we can simplify this and have only L minus 1 theta vectors. And the way we do that is, for any I, we would divide numerator and denominator by that. And one of these guys in the denominator would be canceled out. It would just turn into 1. And the rest of them would be this subtraction. So we see that there's really only... Does everybody see that? Or should I write that down? Write it down, yes? No? Write it down. Okay, so let's see if I did it. Right, so let's add a page. Oh, I should have added it over here. Let's add the page here. Add page before the current page. Right, okay, so let's do this. So we have the numerator, which is the numerator for the ith class, and we have the denominator, which is j is equal to 1 to L of exp of theta j and x. And we multiplied this numerator and denominator by 1 over exp and we divide by the same thing. So we're basically multiplying the whole thing by 1. But that's going to equal 1 over 1 plus the sum for j is equal to 1 to L, but j not equal to I. So it's all of the j's except for j is equal to I. And what we're going to get is exp of theta j minus theta I x. So notice that let's just call this entity here, we can call this guy theta bar j, right? But theta bar j, which is equal to theta j minus theta I, there's only going to be L minus 1 of these theta bar j's. And if L is equal to 2, there's only going to be 1 theta vector. And the only thing that matters is this difference. So it's just exactly what happened in the binary case, except now we've got L of them. And so it turns out that when we do this thing up here, there's really only L minus 1 distinct theta vectors that matter. And to get the L distinct ones, we can subtract any one of them. Notice that I is arbitrary. It doesn't matter which one we do. In the same sense that we could divide it by the first one, the second one, the third one, or up to the Lth one. The main point is that there's L minus 1 distinct theta vectors. Okay, so that's this. So what this uses then is just like there's something we saw, there's the logistic function. This uses something that's known as the softmax function. And it's a little bit funky, the notation, but basically it's the softmax, which is parameterized by this set of scalars, A1 through AL, and it's the ith output of the softmax. So softmax is like it's a vector valued function. It it produces a vector of values. And so what we're doing is we're taking the ith output of the softmax, and the ith output of the softmax is equal to exp of a sub I divided by the sum of the exps of the AIs, or AJs, I guess, in this case, because it's J. And it's parameterized by LAs. I don't mean the city. It's too late for jokes, right? We should just say LAs. And especially too late for bad jokes, like that one.
It's always too bad for bad jokes.
So it's too late for bad dad jokes?
Excuse me?
Sorry, what did you say?
I said it's always too bad for bad jokes.
It's always too bad for bad jokes, yes. So we have L parameters A, and this becomes the softmax function. So this is something that everyone should really remember. Softmax. It's a multi-class generalization of the logistic function. And it's exactly equal to the logistic function when L is equal to 2. Now, one thing you might wonder is, like, why is it called softmax? Well, here's one way of looking at it. When you plot the max, let's say this is the a-axis. The horizontal axis is A. And you plot the max of 0, comma A. So when A is negative, you're going to get 0. And when A is positive, the max of 0, comma A is just going to be the line. It's just going to be the positive part of the line, truncated at 0. So it's kind of like a thresholded linear function, max of 0, comma A. If you do something like, if you take log of exp0 plus expa, that's kind of like a soft max function, right? So it's like when A is negative, then exp of negative A is going to be very small. It's going to be very close to 0. And you're going to take log of exp of 0, right? And what's log of exp of 0? That's going to be 0. So like when A is very negative, it's going to be 0. But then as A approaches 0, this exp starts to become significant, and you slowly start moving up. Until what eventually happens is that when A becomes positive, so by the way, this thing is always equal to 1, right? That's always equal to 1. And so the fact that this is always equal to 1 ensures that this argument is never going to go negative, and ensures that that argument is never going to be 0, right? Because the smallest possible value of the log is going to be 1, and we know that the log of 1 is 0. And so when A is very negative, it's just going to essentially be log of 0. It's the log of 1, which is 0. And so this 1 kind of saves us from trying to take the log of 0 or the log of a negative number. God forbid. But on the other hand, when A gets very big, that same 1 becomes negligible, because it's exp A is going to get very, very large. And exp A is going to be the only thing that matters inside of this argument. And so log is essentially going to, for the most part, ignore the 1 and pay only attention to that. And what it's going to do is it's going to be log of exp of A, which is essentially going to be A. So it's 0 over here, it's 1 over here, and then it has a smooth transition. So you can see that doing things like log of exp 0 plus exp A is kind of like a soft version of the max. Now, in fact, it turns out that if you take the following, you take the ith value of the softmax function, where you're parameterizing it with the same A's, but you multiply it by beta, which is a positive quantity, and you let beta go to infinity. That the limit of, as beta goes to infinity, of this quantity is going to be 1 if I is really equal to the max of the A's. And it's going to be 0 otherwise. So what happens is, very much like the logistic function, what's going to happen is that as the A's get larger and larger in magnitude, the softmax vector output, remember it's a vector output, is going to turn into a one-hot output, where only one of the elements has any value. It's going to be the value 1, and all of the rest of them are going to be 0. And that's going to be the maximum 1. It's going to have value 1 if it's the maximum A. So it's directly analogous to what happened in the logistic case, except now we have, rather than 2 outputs, we have L outputs. And so therefore we can use this as a multi-class probability model. So rather than a binary probability model where we only have one, or 2 outputs, we can have as many outputs as we want. We already talked about binary encoding. And so this becomes our multi-class probability model. We have L possible, we have the probability of Ci given X. That's the probability of class I given X is the softmax. And it's a real, you can really interpret it as probabilities. Now the other thing, why can we interpret it as probabilities? Because no matter what the values of the parameters, so theta in this case, by the way, this theta is equal to this collection of thetas. Theta 1, theta 2, up to theta L. So what this means is that this theta here is really a matrix. Right? So it's a matrix because it's a collection of vectors. Each vector is of length m. So it's really an L by M matrix. And it sums to 1, and you never get an output that's negative, and so therefore it can be validly interpreted as a probability. In fact, one of the things that's really important about softmax is that it's often the last thing that happens in a neural network. So if you have a deep neural network, the thing that everybody wants to learn about, the last thing that happens is you have all this stuff that happens, and then the last thing you want to do is you say, I need to give my neural network a probabilistic interpretation. So what you do is you just feed it to a softmax, and boom, you've got a probabilistic interpretation. Thank you very much. That's the way probabilities work. Now, are they really probabilities? I mean, in some sense, they can be interpreted, and under some circumstances, you can actually prove that it converges to the 2 probability distribution. Very much like the logistic regression case, you can in certain cases. So it's actually not so bad to assume that these are probabilities. Now, how do we train? Well, we use maximum likelihood training, just like before. So the training data is a little bit different. So the y values are, remember we said the y values are integers from 1 to L. But what we're going to do is we're going to treat, so normally what we have is the training data, which is we have x1 and y1, and x2, y2. And let's just, and so on and so forth, and you have x of n and y of n. So this is your training data, and let's say that this was equal to, this training data is equal to, say, whatever x1 is, and let's say that the first y is the label 3, and we have x2, and the second y is the label 2, and x3, and the third y is, say, the label 7. And let's do the last one. So x of n, and the last y is maybe the label 11, right? So we don't know how many classes there are, but there are at least 11 classes here. So what we're going to do is we're going to turn the labels, which is just this part, into a one-hot matrix. It's going to be an n by L matrix. And each row, this is the matrix T. And so we have we have the same number of rows, but we have L columns. And what the columns correspond to is a one-hot encoding of the integer label. And so what this means is the first row will be 0. Let's say that this is 1, 2, 3, up to L. So it's going to be 0, 0, 1, 0, 0, 0. Let me actually make at least 11 columns. Sorry, I'm still not used to this eraser. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So let's just say that L is equal to 11 in this example. And so these are going to be all zeros. And the second one, since the label is 2, is going to be 0, 1, 0, 0, 0, 0, 0, 0, 0. The third one is going to be it's going to have a 1 in column 7. And then the last one the very last one, of course, is going to have a 1 in column 11 since the integer is 11. So we're just representing the labels using this one-hot matrix. And that's what T is. Okay? So why are we doing this? The reason why is for the same reason that when we did logistic regression, it turns out that expressing the maximum likelihood equation and the maximum likelihood solution is going to become very easy. It's just a re-encoding of the data in a way to show mathematically how to learn, how to do machine learning relatively easily. But before we do that, let me just make sure everybody understands what T represents. It's a one-hot encoding of the labels. Everybody have any questions on T? This T here. Okay, so we have different parameters in the model. Now these are each one of these theta j's is an m-dimensional vector. Because remember we said we have L of them. Now we're not going to worry in this case about the redundancy. We're just going to say there's L thetas and we're going to train it in this context. So it's kind of like training like the probability of heads and the probability of tails together, but with a constraint that they sum to 1. And the constraint's going to come for free because of the softmax function. So here's the likelihood. And we can express the likelihood very easily using this matrix notation, because this is T. Because remember, matrix T with entries Tij, lowercase tij. Lowercase tij is either a 0 or a 1. And so mathematically, we can raise something to the power. And if it's raised to the power 0, then it just becomes a quantity 1. It doesn't matter. And if it's raised to the power 1, it actually does matter. So what we're doing is with the likelihood of the training data, which is this, right? Because this quantity here, T and X is the same design matrix that we saw before. T is this new matrix. It's the one-hot representation of the labels. D is the data set, which is the same as Tx. The likelihood of the data given the parameters, which is the thing we want to maximize, can be represented as the product over every single sample. Right, that's assuming the samples are independent. So we take the product over all samples, and then we take the product over all columns of the matrix. And we say, okay, well, the probability of this class, given the input and all of the parameters, but raised to Tij. So if this probability doesn't matter unless J matches the label in the ith row of the matrix. So that gives us a really nice representation of the likelihood, which if we take a log, what's going to happen? If we take, in fact, the negative conditional log likelihood, which is the cost to be minimized, turns into this nice sum thing. It's the sum over all data. There's the negative. This negative is this negative. The sum over all of the samples. The sum over all of the labels. We have the Tijs, which are very sparse. Remember, there's only one single 1 per row, and for every row of this matrix, we've got a bunch of zeros except for 1, which corresponds to the label, and we've got the log likelihood. Now, why do we do this? Because the log of the softmax, this is a softmax model in here. This is softmax. And whenever we take the log of a softmax, it's easy to take derivatives of. We can take the derivatives, we can do stochastic gradient descent, and the gradient of this objective with respect to the jth parameter turns out to be something very similar. It's basically the error, and it's basically saying this is the probability, right? And it's the probability minus the label, right? So for example, if this target, T is the target, if the target is 0 and you're giving that class for this particular x a high probability, you have a high error proportional to how big x is. But if, on the other hand, if the target is, say, 1, if the class is truly 1, and you're giving a probability of 1 or giving a probability almost equal to 1, then the error contribution for that particular sample is 0, right? It's basically saying you're not in error, you're fine, I'm not going to affect the gradient at all, and so the parameters are not going to be affected by the samples that you're doing perfectly well on. You're only going to be affected by the samples that you're not doing well on. And this is the same form of error that we saw before in logistic regression and in linear regression, except it's multi-class. We have this error thing times x. And so from this we can do gradient descent or stochastic gradient descent and so on and so forth. So, and do machine learning and do multi-class logistic regression. So any questions about this? I mean, like other than the gradient, that's the other thing that's kind of beautiful about stochastic gradient descent is that you can have exactly the same learning algorithm for different models and different objectives as long as you have an expression for the gradient. And one of the things actually that has gone into a big part of what modern machine learning systems do is make it really easy to compute gradients. I mean, you don't even, like if you're using like PyTorch and TensorFlow, like it will do the gradient symbolically for you. You don't have to do it. Like I'm old enough now to say back in my day, when I was a student, every time I had a new machine learning algorithm, I had to have to do pages and pages and pages of math to compute these really complicated gradients using the chain rule. And it was extremely tedious and extremely error prone, and I would always make a mistake, always make a sign mistake, and it wouldn't work. Because of one tiny little sign mistake on page 7 of a 20-page derivation. And then you run it, you code it up, it doesn't work, you go through the equations, and you make the same sign mistake again when you go through the equations again. And then there'd be some snarky friend of yours who would say, on page 7 you missed that negative sign, and meanwhile you've spent months of compute time on a bug, on a tiny little sign bug. Anyways, that kind of thing used to happen, which doesn't happen nearly as much anymore because gradients are a lot easier to compute because it's all symbolic. It's all done automatically for you. That's a little anecdote. Anyway, so but that's it. It's still gradient descent. We train it. Now, one thing about logistic regression is that we talked about this idea of a linear discriminant function. So, like this example of multi-class classification, like here you can see that there's a linear separating boundary between the reds and the blues. In the case of 3 classes, this is not a line, right? And this is not a line. These are not linear separating boundaries. So it turns out that logistic regression cannot do this. Logistic regression cannot do a nonlinear boundary behind this. Now it turns out in this particular case, a linear boundary would still work because you could do a boundary that looks like this. Like that could be a line, and this could be a line, and this could be a line. Those are all linear boundaries. But there are some classification decisions, like if we had, like, let's just do another example. Like, let's say we had, let's say the green dots were here. The red dots were here. And the blue dots were here. Right, so clearly no set of lines are going to separate, no 3 lines are going to separate the reds from the greens from the blues. Right, you can't, like, unlike in this example here, where you can draw a line that separates the reds and greens from the blues, this example here, it won't work. Actually, maybe you can see it a little bit better. Can anyone find lines that separate these? No, but you can do it with a curved classifier, right? So like with a nonlinear classifier, because if you said, okay, well that's the separator between reds and everything else, and this is the separator between greens and everything else. And then, then blue could be everything other than those 2 regions inside. So a neural network can do this kind of stuff. Right? A neural network is a very nonlinear model. Logistic regression, unfortunately, despite its ability to generalize to multiple classes, uses linear discriminants. Because remember, in the form of the way that we decide is that we take the dot product between theta j and x, and we find the j that maximizes the dot product between theta j and x. That's how we decide. That's the argmax over j of theta j and x. Each decision is based on a linear discriminant function. And so what essentially we're doing is we're dividing the input space, or partitioning the input space up into L regions. And the winning block, so how do we decide which block is all x in m-dimensional space where the ith linear discriminant function is greater than all of the others corresponds to the region in m-dimensional space that gets assigned class I. So another way of looking at it is to say that the ith region is equal to all x such that this is true. And this is basically just expanding this thing out, right, by taking the difference of these dot products, that this is greater than 0. And that's identical to say all x such that the ith probability is greater than all of the other probabilities. That's after you apply the softmax function. But this is basically a bunch of linear boundaries. These are all linear. This is a hyperplane. That's the equation for a hyperplane. In 2 dimensions, it's an equation of a line. In 3 dimensions, it's an equation of a plane. In 4 dimensions, it's the equation of a 3 space. Right? They're all linear spaces. And so that means that everything that separates one class from the other has to be linear. And so what that would mean is that the way we divide the space, this is kind of out of order. I don't know why it's doing this. The way we divide the space is this. Like if we have lots of classes, we have to divide things into regions, the boundaries of which are lines. So this is a linear tessellation. And in 3 dimensions, it would look something like this. And this is, unfortunately, this is the right one. So in 2 dimensions, you used to have x1 and x2 as the input, and this is the region that the ith class is the maximum class, and that corresponds to a linear function. So like while x is in this region where this ith, let's call this guy the ith one, right? While x is in this region down here, where class I is the decision that's being made, the linear discriminant function is active, and it's a linear face of this convex. This is known as a convex polyhedra. And it's convex basically means because it basically means it's kind of bowl shaped. You can kind of see it in this picture. Hopefully you can see it. Can folks see it in this picture? Yes. So while multi-class logistic regression or softmax regression is powerful in that it generalizes logistic regression to multiple classes, you have to be aware of its limitations, which is that it's only allows linear boundaries between classes, and inside each region it's linear, right? Because it's basically a bunch of linear discriminant functions. Each one is linear in this region. And hopefully you can kind of visualize this. Like this is X space. So X space is kind of like the floor. And then this is the response of all these linear functions. And at every position, no matter what X is, what you're doing is you're taking the max over all of them. And maybe you're aware, but like the max over a bunch of linear functions is a convex function. Like in 2 dimensions, it kind of looks like there's a linear function, there's a linear function, there's a linear function, and there's a linear function. And if you take the max over all of those at every step, you got this, this, and that. And this is convex right here. So that's in 2D. And in 3D, this is the example in 3D here. Because you're taking the max over each one. So every single one of these like little hyper segments of planes corresponds to one of these line segments. So this is a line segment, this is a line segment, this is a ray, and this is a ray. Okay, any questions? We won't, I know it's late and everybody's tired, but I want folks to ask at least 2 questions before we end. Yeah, question.
I think I kind of see it in the 2D version, but do all the regions need to be continuous? Or can you have...
Yeah, they have to be continuous because there's the point, there's this point here, this boundary between when one of them's the max and the other is the max, and there's this going to be point. As soon as you move a little bit over, then suddenly the other one's going to switch in. You can get arbitrarily close where they touch. So it's kind of like intersecting planes, where these planes intersect, and there's going to be the line, like this line is the point where there's a tie. Like all of these intersecting lines, there's going to be a tie of more than one. And it could actually be the case that there's a tie of more than two. In this particular picture, there is no ties of more than two. But along this line, like this is going to be the line here where if we take like x, we take x such that theta 1 and x is equal to theta 2 of x, not theta 2 of x. So the inner product between theta 1 and x and the inner product of theta 2 and x, all x such that those two inner products are the same, that's going to be one of these guys, all right? But the only part that matters in this particular case is going to be this part of it, because somewhere else, like this is the case where this segment here is where they're both the max. And so that, and we can say that theta 1 of x is equal to the max over j theta j and x. So that this expression up here corresponds to one of these guys, one of those line segments. So it's equal and the max. And I think that would, well, officially what I just wrote was not correct. It actually corresponds to this thing down here. That segment in X space, because it's an X space. And in this particular case, X is two-dimensional. So we're down here. And this is the response. This is the output of these dot products. Okay, one more question. Yep. You go ahead. Or why don't you both ask? So, two more questions are better than one more question.
Okay, so you talked about all the limitations of logistic regression. Is there a type of like generally known like if you're I don't know your experience in your job, you kind of like this data type, this type of data will work really well with logistic regression. Is there an example of that or a number of examples of just knowing off the top of your head what type of?
Yes. I mean, it sort of goes together with what feature space you're in, because remember when we looked at this picture here for logistic regression, one of the assumptions of logistic regression for it to be good is that the data is well separated by a line, or is reasonably separated by a line. Like pretty much all logistic regression problems, the only thing it can do is to say, okay, the zeros are on one side of a line and the ones are on the other side of a line. Or if you're in high dimensions, the zeros are on one side of a hyperplane and the ones are on the other side of a hyperplane. There's no way of having a curved boundary. Like you can't, in logistic regression, have a decision region that looks like a decision boundary that looks like that. So if it's the case that your classes are linearly separable, or at least close to linearly, they don't even have to be perfectly linearly separable. Like it could be the case that maybe your greens are over here and your reds are over here. So you can see that there's a few exceptions, like maybe there's one red over there and one green over here. But for the most part, it's pretty well separated by a line. Like in this particular case, you can say, that's a good separator. My error is pretty low. So that in that case, this is the stuff on the right here. Hopefully you can see like all this stuff here. So you can say that in that case, logistic regression makes sense in the current feature space I'm in.
How could you know that by just looking at the data? I mean, is there
You can't know by looking at it, but what you can do is train. Logistic regression is so easy to try. You just train it up, it trains very quickly, and if your classification accuracy is terrible, then you know it's not well. It's not well. I mean, you can even do that in your training data. Like, what if you train your training data and you look at the training error, and the training error never gets below 80%? Then you know that the data is not linearly separable. And so, and that's really, in Python these days, it's like a few lines of Python to do that, and you are learning how to do that now. Now, there's several ways of dealing with it. One way is to say, okay, well, it's not linearly separable in the current way I'm representing my data. I could add more features. Like you could add x1 squared and x1 x2 and x1 squared x2 cubed, and so on. You could start throwing features at it, and that's a very potentially useful way, but also a very old-fashioned way of solving the problem. It will help eventually, and you will start better separating your data. The more modern way, the neural network way, is to go to a nonlinear model. Right? Why should you waste your time? Why should you waste human time throwing all sorts of features at the problem? You don't know precisely which ones. You can just throw a ton of them on, and it might be too many. Some of them might be useless. Some of them might be useful, but maybe none of them will be useful. Or maybe they'll be useful, but they're not the most efficient way of doing it. Maybe there are more direct ways. And so the idea of a nonlinear model is to say, well, let's learn the features. Let's learn the appropriate transformation of the input space automatically. And that's the idea of learning representations, which neural networks, some partially attempt to do. They say, well, look, we have all this nonlinear power. We're going to learn, part of what we're going to do, especially in the early stages of a neural network, we're going to learn a nice transformation of X to some other space. And when you look at the last layer of a neural network, it's just a linear classifier. Like the final layer of a neural network is just logistic regression. And so all that work, you have 200-layer neural networks. So you have 199 layers that are just doing a nonlinear transformation. So the final layer is like logistic regression or softmax regression. And so you can kind of think of it as everything but the last layer is just doing feature extraction. And then the last layer, everything's nicely linearly separable. And so the more modern way of thinking about it is let the machine, we have lots of data, we have lots of fast compute. Let's let the compute do the feature learning for us. And that empirically has proven to do pretty well, because it kind of works. And so a lot of people are using neural networks just for doing feature extraction. And you had one last question. Or did you turn into a pumpkin?
I could. That might happen. But quick question was like when you're discussing your Voronoi diagrams, what's the relationship of this to like vector quantization? I mean, they seem kind of similar.
Yeah,
Is that fair?
Yeah, no, that's a very fair question. It's like and you're right, because like we're using even the Voronoi diagrams, the terminology we're using is something that's actually used in vector quantization. So oftentimes, like what you might do is then decide that everybody in one of these regions, since they're given the same classification output, let's just use this as a way of integerizing our features. Like you might start from X being real values, and you might just use this as a mapping to something that quantizes things, so that you no longer can make a distinction between this and this. That's what a quantization is, right? And it's Voronoi, right? The Voronoi diagram, because it's saying, that's the Voronoi tessellation. So it's basically saying that after you've quantized, anything in this pink region you can't tell the difference between, and anything in the red region you can't tell the difference. That's the quantization process. Just like any quantization process, where if you're quantizing a scalar, anything between here and here are treated the same.
Right.
Even though if it was a true mathematically real number, you'd have infinite precision. So this is exactly vector quantization if you were to use this to quantize. But oftentimes you do VQ for different reasons. We're using the same kind of tools for visualization that are often used for vector quantization to explain how softmax regression tessellates the input space in terms of these linear boundaries.
Typically, the vector quantization is used for compression.
That would be,
That's the biggest-
it's used compression, it can be used for noise reduction, it's lots of things you do use VQ for. But it's similar, and you use the same kind of diagrams. In fact, this person's name pops up there a lot.
Yes.
Yeah. So, all right, well, thanks for staying here, and I know it was a marathon, but you guys did it, and you don't have to come back here for a week, which is great maybe for some of you, but I'll see some of you on office hours on Thursday night.